All right, 10:25. I think we should start slowly but surely. Got some people in the room. Uh, okay, so my name is Łukasz Piątkowski. Look at the Institute of Physics here at the University of Technology, and it is my pleasure to share this first of two sessions today. Um, and this one is dedicated to materials engineering and physics. So we have seven scheduled. The last speaker of the session is not present, so we don't have such a huge pressure when it comes to timing. But nevertheless, I will, if someone will be getting closer to the time slot, the end of the time slot, I'll just be waiting. Okay, so the speakers kind of try to pay attention, or I will pay attention. Um, so we have seven blocks. Um, the session will last with 1 to 20. And for your information, after that section, there will be lunch downstairs, which is where we have coffee, where the posters are hanging. Okay? I think that's about it when it comes to technicalities. So the first speaker, so we have one invited speaker and then six contributors. The invited speaker is Mr. Daniel Mikin, sitting here in the front row. He comes from Czech, Prague, um, from the Charles University, and he will be talking about particles from the gas state for advanced applications. So it's a very nice talk. I'm sure it's combined materials engineering, nanomaterials, and I guess application for well, multiple applications.
Several applications.
Right. Also including those related to bio. So I think it's a very nice talk that will combine branches of science, physics, engineering, and so on. So, Daniel, the floor is yours.
Thank you very much, dear Chairman, for the kind introduction. I would ask you if I will use the microphone, will it be fine? Can you hear me?
Yes.
That's perfect. Perfect. So I will speak louder without microphone.
There is a live screen.
Ah.
Yes,
Ah, okay. So they will not hear me without microphone. Okay, I see. Then I will speak using microphone. Maybe I will be too loud sometimes. Uh, yeah, thank you for the kind introduction. And first of all, I would like to thank the organizing committee for inviting me to give you my talk, which will be about the nanoparticles produced from the gas phase and their use for advanced application. I will show you several applications which we are working on in our lab. So I think all of you know what are the nanoparticles. Nanoparticles are the objects with a size ranging from 1 to 100 nanometers typically, and they can be produced of metals, of dielectrics, semiconductors, and there are also nanomaterials which can be classified as nanoparticles, which are, for example, nanotubes and black carbon. The properties of nanoparticles sometimes overcome the properties of their bulk counterparts. That's why the nanoparticles are now applied for a wide range of applications. I will not call all of them. You may see here on the scheme how many applications were developed for the nanoparticle. And such a huge range of applications, of course, requires the huge number of methods for nanoparticles fabrication. The most popular is the chemical synthesis of the nanoparticles when we mix together several substances and typically initiate the reduction reaction inside the solution. When the metal ions are reduced to metal atoms, which then uh, form the nanoparticles by the nucleation and growth processes. Also, several physical routes for the nanoparticle fabrications were developed, which do not include any chemical reactions. I would show you one example, which is now very popular. This is the laser ablation of metal target inside the liquids as well. So there is a metal plate inside the liquid, which is irradiated with intensive laser light to produce the metal atoms, which again nucleate and form nanoparticles inside the liquid. So these are the typical ways for the production of nanoparticles. Of course, there are many other methods. Here there are just several examples. Physical milling of powders, This biosynthesis, where we use the biomaterials as a precursor for the reduction reaction and for the fabrication of typically metal nanoparticles. But also, you cannot see here, but here should be plasma-based methods. And I will speak in my talk mostly about one plasma-based method, which is called the gas phase synthesis. Unfortunately, all these methods have their disadvantages. If we are speaking about the chemical fabrication of the nanoparticles, always some chemical residuals and chemical linkers are presented inside the solution. Chemical residuals, I mean the product of chemical reactions, and the chemical linkers are used for the stabilization of the nanoparticles. If we need to use the nanoparticles in electronics, for example, we need to additionally purify them to remove these chemical additives. In physical route, we produce pure nanoparticles without any chemical residuals and mostly without linkers. But the problem is related to the control of the nanoparticle properties. It is very hard to control the chemical composition of the nanoparticles if we want to produce with physical route some compound nanoparticles, for example. And also, typically, nanoparticles produced by the laser ablation are very small, so their size is less than 15 nanometers. But some particular applications require the bigger nanoparticles. And I will show you one of these applications today in my talk. So, other methods were developed for the fabrication of the nanoparticles, and one of them was developed in 1991 in Germany by the professor Helmut Haberland, who constructed the first gas aggregation nanoparticle source. The gas aggregation nanoparticle source, this is a plasma-based method, and it is based on the magnetron sputtering. So we use the cathode magnetron to ignite plasma. Why it is called magnetron? Because this cathode contains the magnets inside to densify the plasma and to improve the sputtering rate of the material. In case of aggregation source, this cathode, this magnetron, is installed inside the vacuum chamber, which is called aggregation chamber, with water-cooled walls and with a small orifice on the end. This gas aggregation cluster source is connected to the vacuum deposition chamber where the substrate is located. So this is the vacuum-based process. We need to pump to evacuate the system to obtain the pure nanoparticles. You may ask, why do we need the orifice? We can perform normal magnetron sputtering and to fabricate. What can we fabricate? We can fabricate thin film, or we can fabricate nano islands, for example. But we want to produce nanoparticles. To produce nanoparticles in the gas phase, we need to reach the supersaturation condition. The sputtering is performed in the atmosphere of argon, and the argon pressure inside the aggregation zone typically reaches several tens up to 100 or several hundreds of Pascal. Why do we need the elevated pressure? Because we need to ignite the interaction between the sputtered metal atoms from the target in the gas phase, not on the substrate. To produce the nucleus, the dimers, then trimers. These dimers and trimers, they collect additional atoms and first the cluster grows and then the nanoparticles is forming. The nanoparticles are forming in the gas phase here. And then with a drag force, with a gas flow, they leave the orifice in the form of nanoparticle beam and can be deposited onto the substrate. The substrate could be any vacuum compatible material. So it could be the silicon wafer for semiconductor industry. It could be polymer substrate, like for example, polymer foil or polymer textile or polymer mesh, and even vacuum compatible liquids. And later I will explain you what I mean when I'm speaking vacuum compatible liquid. Which nanoparticles can we produce by this method? The simplest case is the metal nanoparticles, because we need only sputtering of metal target in the argon atmosphere. Here there are several examples from our lab: silver nanoparticles, zirconium, titanium, and hafnium, so transition metal nanoparticles, but also there are many others. We can produce magnetic nanoparticles, for example, nickel, cobalt, or iron nanoparticles. We can produce the nanoparticles of precious metals like gold, platinum, or palladium, which are interesting for catalysis applications. This is the simplest case, but what will happen if we will mix argon with some additional gas, like nitrogen or oxygen, the so-called reactive gases? We can produce oxide or nitride nanoparticles, and here there are three examples of transition metal nitride nanoparticles which we produced in our lab: titanium, zirconium, and hafnium nitride nanoparticles. We can exchange the metal target with a polymeric target, and to perform sputtering not in the direct current conditions, but in the radio frequency discharge. And we can produce polymer nanoparticle, for example, nylon nanoparticle, you can see here. We can admix to argon not nitrogen or oxygen, but we can admix vapors of organic precursor. And we can produce the core or multi-core shell nanoparticles. We can use several magnetrons inside the one chamber, and we can produce the Janus nanoparticles when half of the nanoparticle is composed of one material and half is composed of another material. Or we can produce by the same way, for example, core shell nanoparticles as well. Here there is an example of silver. Okay, colors are not seen very clear, but the blue color corresponds to the copper and red color to the silver. We can deposit into not only on the rigid substrates, but also into the vacuum compatible liquid. When I speak in vacuum compatible liquid, I mean that this liquid has vapor pressure, typically less than 10 to minus 3 Pascal. The example of such liquid is polyester glycol, well-known biocompatible and biodegradable liquid polymer, but also it can be ionic liquid, it can be silicon oil, paraffin, and some other liquids. So instead of the substrate, we put a petri dish filled with liquid, and we deposit the beam of nanoparticle into this liquid. Unfortunately, the diffusion rate of nanoparticles in the viscous liquid is very low, so the particles can agglomerate near the interface between the vacuum and the liquid. That's why we need to introduce the additional ultrasonication step to disintegrate the agglomerate here. And now I will show you some examples. If we use the plasmonic nanoparticles, optically active nanoparticles like copper, silver, and gold, or zirconium nitride, we can produce very nice polarized solutions of nanoparticles. For copper, it is greenish; for silver, yellow; purple for gold; and bluish for zirconium nitride. The optical absorption spectra demonstrate the absorption bands corresponding to the plasmon resonance of individual types of the nanoparticles. By mixing different types of nanoparticles together, we can tune the color. For example, here we simultaneously deposited silver particles and copper particles into the one vessel with polyethylene glycol, and instead of greenish and yellowish colors, we obtained the bluish bimetal nanofluid. This was about the fabrication of materials, and now I would switch to some applications which we are working on in Prague. And first application will be the application of transition metal nitride nanoparticles for solar light absorption. The transition metal nitride nanoparticles are known by their optical properties, so these are plasmonic materials, but also they are so-called refractory metals. So they retain their properties at elevated temperatures up to several hundreds of degrees Celsius. So they are very interesting for the high temperature or thermal applications. By the mixture of nitrogen to argon during the sputtering, we were able to successfully produce three types of nanoparticles: titanium nitride, zirconium nitride, and hafnium nitride. Nanoparticles, here you may see the tunnel and electron microscopy images with the EDX maps. The most important information for us was obtained from the X-ray diffraction patterns, because by the X-ray diffraction we confirmed that we obtained stoichiometric nitrides of these three transition metals. All these metals deposited onto the quartz glasses and inside the liquids demonstrated the absorption band in the red and near infrared region corresponding to the plasmon resonance. But these metals are, or these nitrites are also very interesting because of their efficient solar to heat conversion coefficient. It was theoretically predicted, but the experimental works not so many about these uh, materials, and nobody demonstrated the in-liquid efficiency of these materials for solar to heat conversion. We decided to test our nanoparticles, which we produced on a fluid prepared by the deposition of the nanoparticles into polyethylene glycol, and we irradiated it with solar simulator and measured the temperature with the thermocouple. Here there are the kinetic curves, and you may see that for all three types of nanofluids containing the nanoparticles, the heating rate and the overall temperature obtained after 60 minutes of radiation was higher than the temperature of polyethylene glycol without nanoparticles. And the efficiency of solar to heat conversion increased from hafnium nitride to zirconium nitride to titanium nitride nanoparticles, which confirmed the theoretically predicted results. I would also emphasize that the concentration of the nanoparticles in this solution was only 50 micrograms per milliliter. So by increasing the concentration, uh, even by 10 times, for example, we can heat it up to the much higher temperatures and much faster. Another topic which we are working on now in our group, and this is one of my main topics of work, is application of the gas gated nanoparticle for neuromorphic engineering. Neuromorphic engineering, what does it mean? Now you know very well the artificial intelligence, and we had a huge lecture about the artificial intelligence today. It becomes more and more important. But all modern artificial intelligence systems are based on the classical silicon-based electronics, silicon-based computers, which consume a lot of energy for the solving quite normal tasks like the text fabrication or processing or the image generation. But can you imagine that our brain can perform even more complex tasks like image recognition or speech recognition, consuming only 10 to 20 watts of power? So our brain is the most powerful computing system in the world. And this is because of the unique properties of biological neural networks, which are the plasticity, self-organized ordering, adaptivity, and three-dimensional connectivity of the neurons. Nowadays, scientists are trying to implement these principles in the device. And they found that the device, which is called memristor, simulates very well the performance of synapses. Synapses are the connections between the individual neurons. What is the memristor? Here there is a typical scheme of the memristor. This is a sandwich device composed of two electrodes with a dielectric in between. When the electric field is applied to this device, the conductive path forms between the electrodes. This conductive path can be based, for example, on the ions released by the biased electrode diffusing to the grounded electrode, reduced there, and the metallic filament is formed. When the metallic filament is formed, the current passing through the device increased by several orders of magnitude. This current is very high until the filament will not be disrupted, for example, by Joule heating. When the filament is disrupted, the current decreased by several orders of magnitude. This event is called switching on event or transition between the high resistance and low resistance state of the device. And this event is called the reset event or the switching off, the transition between the low resistance state and high resistance state of the device. How can nanoparticles be implemented in the memristors? For example, to simplify the process of the filament formation, we can add, and our colleagues from Germany did this experiment, introduced the silica gold nanoparticles into the silicon oxide dielectric matrix, and you may see that the switching events from high resistance to low resistance state and back occur at very low voltages range, less than 1 volt. This is because the filaments are forming not between the electrodes, but between the nanoparticles which are already pre-introduced into the matrix. Another topic which is now becomes more and more popular is the percolating nanoparticle networks. And also our colleagues from Germany work on this topic already several years, when the nanoparticles are deposited not on the sandwich structure, but on the planar substrate equipped with the planar system of the electrode. The deposition is stopped in the so-called closed percolation regime when the aggregates of nanoparticles are separated by the atomic scale gaps. When the constant electric field is applied to this network, for example, 5 volts, the atomic scale filaments form inside the gaps. And when the individual filaments are formed, the spikes are observed on the temporal dependence of resistance. Each spike corresponds to the formation of individual filament. The interesting was that they analyzed the spatio-temporal correlations of the spiking events, and they found that they are similar to the firing burst mechanism in biological neurons. So they were able, using nanoparticles, simulate the processes of neural transmission inside the biological neural networks. But the problem is that the classic memristors and the percolating nanoparticle networks are solid state. But our brain definitely is not the solid matter. It is quasi-liquid matter. That's why we can produce, our neurons are three-dimensionally organized. So we thought how to transfer this knowledge of the percolating nanoparticle networks into the liquid, and we came up with the idea to use the nanofluids prepared by the deposition of nanoparticles into the liquid dielectrics. We use the similar substrate, so planar substrate equipped with the electrode, and we put on the top the droplet of nanofluid produced of silver nanoparticles deposited into the polyethylene glycol. We applied the potential between the couple of neighbor electrodes. One was biased and another one was grounded. And during the applied potential, we controlled the processes in the nanofluid using the optical microscope. First of all, I would mention that we characterized the potential of the nanoparticles, and it was found to be minus 32 millivolts, so our nanoparticles are negatively charged. When we applied, when we recorded the current voltage characteristics for pure polyethylene glycol and polyethylene glycol with nanoparticles, we observed that in PEG, we did not see any resistive switching. We did not see any increase of current by several orders of magnitude, and the overall current was very low in the range of microamps. But when we introduced nanoparticles after the threshold voltage of 4 volts, we observed the increase of current by 2 orders of magnitude at positive polarity of biased electrode, and then the decrease by 2 orders of magnitude at the negative polarity of biased electrode. We observe similar switching events at higher voltages, 5, 6 volts, and we ask ourselves why do we observe the switching events inside the nanofluid? We took a look onto the videos, which I want to show you here. The left electrode is biased and the right is grounded. And you may see that at the positive polarity of biased electrode, the conductive path based on the nanoparticles and nanoparticles agglomerate grows in the direction of the grounded electrode. Uh, I would start the video again. Yeah, so in the beginning, we still have the gap between the conductive path and the grounded electrode, but when we apply the positive potential, you see that the conductive path start to grow. And at the moment when the conductive path attached to the grounded electrode, we observe the first switching in the system. This video is overlapped with the electric field model, and you may see that this path is located in the area with the strongest gradient of the electric field, reaching 1 million volts per meter nearby the tip of the electrode. The most interesting for us was that when we applied the constant electric potential of plus 6 volt to the already preformed filament, we observed similar switching, similar spiking behavior as was observed by our colleagues in solid state percolating nanoparticles networks. The second very interesting thing was that our path grew not only in 2 dimensions, but in 3 dimensions. And here you may see the out of focus photo made by optical microscope. Additionally to the conductive path growing in the plane of the electrode, there is the second path growing out of plane. So in this liquid system, we can, in principle, realize the three-dimensional conductive networks with the same functionality as biological neurons. This slide I called perspectives and problems instead of the conclusion because we, of course, can produce different types of the nanoparticles with this method. More and more applications of the nanoparticles appear, more and more groups in the world use this technology for the fabrication of the nanoparticles. But there are some fundamental problems which should be solved to push further the application of the nanoparticle sources. And the main problems are the insufficient deposition rate for industrial applications and the low target material utilization. We sputter the metal target and we produce the erosion track. So we consume around 9% of material and then 91% is going for the recycling. We need to improve this somehow. And that's topic which we are also working on in our lab. And we developed different types of the magnetron. Instead of the planar target, we use the cylindrical target with the rotating magnetic circuit inside. So plasma regions are rotating around the target and sputter the full surface of the cylinder. Cylinder could be uh, any length, any diameter which you need. By this, by the use of this magnetron, we increased by several times, uh, 10 times the deposition rate of the nanoparticles. So now we reach several tens of milligrams per hour in case of the metal nanoparticles. And we can also produce different types of the nanoparticles. For example, when we use the composite copper silver target, we produce the composite nanoparticles, Janus type nanoparticles, or even core multi-shell nanoparticles. And we can also admix nitrogen to the argon during the sputtering and produce nitride nanoparticles. At this moment, I would acknowledge the financial support from the Czech Science Foundation of this project. Some of projects are currently running. I would acknowledge our group, our PhD students for their hard work on this project. Also our international collaborators, and I would mention that we are open for any collaboration. If you are interested, please do not hesitate to contact us. And also the last thing, we are hiring new PhD students and postdocs in our group. So if you are finishing your PhD or your master and you are interested in working on the nanoparticles, do not hesitate to contact us and visit our webpage. Thank you for your attention.
All right. Thank you very much, Danny, for this insightful talk.
Thank you.
So basically, if anyone is in need of particles, this is the guy to talk to. Any questions? So the conference is for the benefit of the youngest researchers, bachelor, master students, PhD students. So I expect a lot of questions now. Okay, there we go.
Yeah, thank you. Your presentation was very interesting, especially
Thank you.
this narrow information. Could you specify or have two short questions?
Yes.
Could you specify like the range, like how big and how small it from this nanoparticles? And second of all, like how would you compare your methods with all these methods you mentioned before, like physical?
Thank you for the questions. I really like both of them. So first, about the size of the nanoparticles. With a simple type of cluster source, by changing the, I will show, yeah, for example here, we can change the size of the nanoparticles by several methods. So we can tune the current, input power in plasma, we can tune the pressure, and we can tune the distance between the target and the orifice, so the residence time. And by this method, we can tune the size from several nanometers to several tens of nanometers, let's say 50, 60 nanometers in diameter. But recently, our colleague found the way how to trap the nanoparticles by additional discharge longer in the aggregation zone. And now he is publishing the paper about this method. He is able to prepare nanoparticles of size up to 200 nanometers. But the smallest in our case is several nanometers, let's say 5, 7 nanometers in diameter. This is about the sizes, and the second question is about the comparison with different methods. From the point of the production rate, we are far below than the chemists because they can produce grams, tens grams per day. We are limited by tens milligrams per hour. But for some applications, when you do not need uh, really a lot of powder, when you want to produce the coating on some material, I would say that our method is simpler because we do not need spin coat the nanoparticles on the top. We do not need buy them. We can just introduce the substrate inside our chamber and deposit the homogeneous layers of nanoparticles. One layer, less than one layer, or many layers. As I said, it is quite facile because we can easily change the distance between the magnetron and the orifice just manually. We can easily, just by pushing buttons, increase the sputtering current or increase the pressure inside the aggregation chamber. So I would say that this is quite facile.
Thank you for your excellent talk.
Thank you very much.
I have one question about the Janusz nanoparticle.
Yes.
I wonder if you can control the layer that you are making. So if you can, for example, go with some part further layers, you can make many layers, or mm, does it work like that?
With the young nanoparticles. Yes. We can. The deposition rate was quite high, so we can produce many layers with nanoparticles.
Okay, so you can make like sandwiches and only from two materials or unlimited, like.
Thank you for the very nice question. At the moment, uh, okay, we can use several cluster sources to produce the layers of individual nanoparticles. So we can use 2, 3 cluster sources. Of course, the deposition setup will be huge, but we can do this. If we speak about the mixing in one nanoparticle several elements, now we have results for only 2 elements. But you, I think, know that the topic of so-called high entropy alloys now is increasing in the world when people want to mix in the alloy 4, 5, 6 elements, and we are starting to think about this. So to introduce several magnetrons into the one chamber and to prepare the multi-component, really multi-component nanoparticles.
Any other questions, comments? No? Then I will chip in. So the first one is very easy. Did you characterize the distribution of the sizes?
Yes, we characterized.
So homogeneous it is.
Speaking about the small nanoparticles, small, I mean less than 20 nanometers, the distribution is plus minus 3, 5 nanometers. So let's say 5 to 15%. Speaking about bigger nanoparticles, the distribution becomes much broader. But there are special additions to the cluster sources which allows to filter the nanoparticles by size. But with the filters, we reduce the deposition rate by by factor of 2 or even bigger. Yes.
Okay, and the last one, if you can go one slide back, or maybe 2 slides then,
Yes. Here.
where you have the resistivity plot that have spikes.
Yes.
3 slides.
Yes. Here.
For instance, this one. Yeah. So I understood that when you form the filament,
Mhm.
the resistivity jumps to
Yes.
high value.
Yes.
Why doesn't it stay at that value? This means if you see spikes with a temporal trajectory, this means that they form and break immediately.
Yes.
It's not stable. So
Yes.
you form and they break.
You are absolutely right. And this is the advantage of this system, the randomness, because our neurons, they are also not stable. They are quite random. And this is their huge advantage.
Is roughly
They,
constant over time.
yes, here we cannot control the number of these gaps. and this is the difference from the biology actually. But you're absolutely right. This is the random spiking, but there are spatial temporal correlations between the inter-event intervals that are similar to the biological. Again, at some range of approximation.
All right. Okay. Last chance. Yeah.
Can you control these nanoparticles down to the specific nanoclusters in the magic numbers? Would you be able to study the magic number formation plus?
At the moment, no. This is more kind of playing with the parameters. Yes,
5 years time.
yes, we still have some time.
All right. Let's thank Daniel again.
Thank you very much.
And and I'm ask the next speaker, Grzegorz Urbaniak, who will talk about the possibilities of measuring effectiveness of attenuation of low frequency magnetic fields by modern construction materials. So again, materials engineering, broadly speaking.
but much more practical, I suppose, because I'm from other discipline. I'm electrician guy,
Okay.
and magnetic fields are every around my job, my interesting, and I would like to fight against magnetic fields
I see. Okay. So they want to
using
magnetic fields around numbers you want to destroy. All right.
yes.
Very cool. The floor is yours.
Okay, good. I suppose afternoon. Afternoon. My name is Grzegorz Urbaniak. I'm a PhD student on Poznań University of Technology, and I'm working in company Astad, what is responsible for delivery electromagnetic compatibility test system and about radio frequency and other topics around the electrician and fields. Uh, Today, I would like to tell about some part of my work in PhD activity. This is the test bench for magnetic field attenuation of materials for low frequency. Uh, on the beginning, magnetic field is everywhere around us. It could be uh, made by natural or made by humans. Uh, this magnetic field are emission for the environment. And this environment we can separate for two types. First, it's environment what is allow for every people, and second one what is allow for just the workers, special areas, special environments. My interesting about equipment about what is areas. It's elements what are connected for the power grid, especially 50, 60 hertz, and of course we have higher harmonics of this. Inverters, drivers, especially for mobility, and machines what using magnetic field, especially for heating. Uh, if we are talking about machines what emitting for environment magnetic fields, these fields are limiting based on different standards. Uh, for example, standard this one uh, giving for 50 hertz different levels for these two environments, what I mentioned before. And as you can see, these levels of limiting are 5 times different. It means for uh, civil environment, it's much more lower than worker environment. In Poland, we have our own uh, regulation. Uh, Here is for normal environment. You can see exactly magnetic field level for 50 hertz, and in example for third harmonic. what is generating too, because there is the phenomena of saturation and other things about magnetic fields. And as you can see, for the higher frequency, this level is much more lower. Here is much more complicated because this is the regulation for the work area. There is a few of zones what limiting the field, what could be access for these zones, and other things. But as you can see, here is much more higher limits of what is allowed emitting for this for this environment. Okay, now we have two sides of the situation. It means we have equipment, we have machines what generating magnetic field for environment, and we have limitations of this level of magnetic field. It means sometimes it's not compatible. It means we should to find the way, the materials what are able to mitigate this magnetic field. And this is the part of this presentation. This is the test bench for measuring magnetic field mitigation of the material for the low frequency of this magnetic field. This is the first part of this test bench. This is the coils working in the hand-pulse coils system. Here you can see test methods, what we use to validate this coil. We validate in two areas. This area it was uniformity area. As you can see, the cube with length of the edge 60 centimeters are still uniform. It's quite big. It means it was one of the goal of our idea to give the possible to testing quite big construction. The second part it was parameters what called coil factor. As you can see, it was 41. It's really good parameters for these coils. Next part for this test bench it was measuring equipment. We using two magnetic field equipment for the measurements. Both of them could be accredited calibration in laboratory. As you can see here, it's our own construction of magnetic field source, just to check correct measurements of the magnetic field equipment measurement, just to prove this part working correct. Last part of the test bench is a special special shielded chamber, shielded cabinet with a window for mounting the samples of the material. This window now has 8 for 8 centimeters. It's relatively small because the samples what we are able to get are small. The best samples will be flat samples with dimension 10 centimeters for 10 centimeters. Here you can see a result of our modeling. And as you can see, here is the measuring window. Here is the field in external. And as you can see, this field from external goes inside the chamber. What we are able to measure this field. And the method of this measurement based on situation when we make two measurements. First without sample, and second one with sample. The difference between these two measurements is attenuation of the material. Here is the ready for measurements test setup. In the end, we are able to measure 200 times mitigation of the magnetic field by the material what is located in this test window. I've made a lot of measurements using this test bench, there is the result of materials what are kind of mesh of not ferromagnetic materials. And here, as you can see, the mitigation is almost nothing, what we expected. But the second measurement was ferromagnetic materials, and here we can measure almost 50 times mitigation of the magnetic field for these materials for 50 hertz frequency. I would like to explain and show some applications what we use this test bench. First, it was uh, machine what using a customer who use on the manufacturing side machine what using magnetic field for heating some elements, and unfortunately they has crossed limits around this machine. Next requirements from the customer side, it was visibility of this shield. He must to see what happens behind our shield, and that was our idea to make holes. The first samples what we prepared it was square, the second it was circular, and in the end we make measurements, and the square holes it was much more better. There is the real uh, execution of this idea. It looks like this. Customer is now uh, happy about his area of the working. It's now fulfills the standards, the requirements, and we are waiting for next order for the next machine. Uh, the next application, it was a question from our workshop, our designers and technical guys about question what kind of accuracy of the execution of the elements of shielding they must do make using some machines on our workshop. Uh, I've made a lot of measurements using two part of these different materials and make here the different gaps. The conclusion of this measurement was accuracy better than 0.3 millimeters because the gap must be lower than 1 millimeter. About the development of this test bench, a few weeks ago, we start the measurements of attenuation in frequency domain. As you can see, it's from 2 hertz up to even 20 kilohertz frequency. If somebody would like to know what the attenuation depends on the frequency range, we are able to do this. This is the result of some kind of configuration of our samples. Next development is to increase the window because we need to develop some kind of connection, the element of our shield, and we need a much more bigger samples to measure. And as you can see, it's even more than half for half meter. Thank you for attention. If somebody would like to check your material about the magnetic field attenuation, this test bench is less than 100 meters from here. Yes, of course.
Thanks very much. Are there any questions? Comments? Yeah.
Okay.
The limitation of the size, because exactly showed I think was pretty huge. So,
Limitation of the size of the sample depends on the wall width window. On this time, we have this small window because the samples from the market, what we can get for cheap or free, are really small. But next removable, and we are able to prepare different this wall with the bigger window too. And we do this, I suppose, till end of this month, and start the next test with our samples because we prepared this.
I have a quick question. In the beginning of the talk, you gave these limits, these thresholds that people can be exposed to. So normal people, like the operator of machines, so myself, I can be exposed to something like 50 microtesla, yeah, or 75 microtesla, right?
Yes, that's the Polish.
Does this take into account the time of the exposure?
No, time of exposure.
Exposed the entire day.
Yes, true. Time of the exposure is given just for these two, the highest for the workers. There is limitation of the time what is exposure for the film. Yes, yes. This is the same idea.
All right. Let's thank you again.
Thank you very much.
And the next speaker, Maciej Żukowski, who come to the stage. We'll quickly switch the presentation. And now we are going to hear something about Raman spectroscopy, or Raman spectroscopy of future potential photometers.
Yes, please.
You got it.
Not that. Oh, this one is for. It was not that. Maybe that's the one that's not work. Yeah, it's fixing course. Maybe you have a pen drive. And yes, take a jump to take it. That I'm not prepared because I also have a PDF version. So.
What would be a conference without technical problems?
Yeah, precisely. First conference and first technical problem. It's a good beginning. I think because I made it an open office impress, so because it's maybe not so compatible with it's yeah. Okay, now it's visible. Maybe you have some like okay, but I think we that's a 3 points, right?
Yeah.
But I guess we will need to use the scroll mouse to jump to the next slides. I think so. Okay. It should be like reading or something like that, I think. You can check quickly. Or something like that. Because that's it. Okay, I think we have to use it like that.
Does it work with scrolling? Does it work with
Yes. Like,
oh,
okay.
okay.
So I think
Now it's
we move the so I will use the scroll.
yeah.
Yeah. So firstly, I would like to thank for a very kind introduction, dear professor, and I would like to introduce myself also. My name is Maciej Rzeczkowski. I'm a student here at Poznań University of Technology. My main interesting zones are Raman spectroscopy. That's why today I'm gonna present and give a talk about our recent research about the application and Raman spectroscopy investigation of type 2
indium arsenide, gallium antimonide superlattice photodetectors that were electrochemically passivated by octadecane thiol. And to begin with, I will quickly explain what really superlattice is and how can we compare it to a typical solid state physics known Brava type of lattice. Because as you can see, superlattice is defined as a periodic structure that is made of different materials, different crystal structures. So it's a layered material. In solid state physics, we have something like a crystal structure that is a highly ordered arrangement of repeated atoms, molecules in three-dimensional space, and it forms a crystal structure and the Brava type of lattice. And as you can see, as superlattice, we can say it's really same, but instead of atoms, molecules, we have like layers of materials, crystal structures. Like on the pictures, you can see we have red and blue layers of different materials, which are also semiconductors. And superlattice could be a three-dimensional structure and also lower dimensional structures, such as an array of quantum dots or quantum wells, which refers to one-dimensional or even zero-dimensional or two-dimensional structures. And like I said, superlattice could be described as an arrangement of crystal structures, that is a layer structure. And but to make it simple, I would think it would be easier to compare it to just a sandwich. So the next, I will talk about what really etiols are and why we have used it to uh, create a passivated layer on the semiconductor surface. So ethiol, as many of you probably know, is an organic compound that has an sulfur hydrogen group and also have the R group, which represents an alkyl or other organic substituent. And like I said, a SH functional group itself is referred to be called as a thiol group. Generally speaking, in solids and liquids, hydrogen bonding between individual thiol groups are rather weak. So the primary force holding the molecules together, the thiol groups, are van der Waals interaction, which also arise due to highly polarizable divisions for atoms in the thiol groups. And why we have found it interested to electrochemically passivate the thiol layer on the semiconductor gallium antimonide surface, because electrochemical passivation provides protection of the surface of the semiconductor from the exposure to ambient atmospheric conditions. Also, it makes possible to reduce the necessity of unwanted electronic surface states, and also it enables us to create a barrier for electron transport from the near surface area to the passivating layer. And on the picture, you can see structural and molecular formula of used thiol layer, which was octadecane thiol ODT. So as you can see, it has a visible sulfur hydrogen group, which is qualified as a thiol molecule. Okay, so to be sure that everyone knows what I'm really talking about, short explanation what really Raman spectroscopy method is. So the Raman spectroscopy is a method, non-destructive test method that is based on the phenomenon of radiation scattering. And when the sample absorbs the incident light, it could be scattered in three different ways because we have three different components of Raman scattering. First one, the most intensive, is an elastic component of radiation scattering. It's a Rayleigh scattering. And other two non-elastic components are anti-Stokes and Stokes Raman scattering. Mostly in our optical measurement setup, we use a specific Rayleigh line cutoff, Rayleigh scattering component cutoff, because it's several magnitude greater in intensity than Stokes or anti-Stokes Raman scattering. And because Stokes Raman scattering, mostly we observe Stokes Raman scattering because it's rather intensive than anti-Stokes Raman scattering. And why? Because as you can see in Stokes Raman scattering, we start from when the sample absorbs the incident light from the ground state, it gets the energy to jump into virtual energy state, and later it relaxes by emitting a photon to one of the excited vibrational energy states. So the emitted energy is less than the absorbed energy. And in anti-Stokes Raman scattering, we start from the vibrational excited energy level. We jump to the higher virtual energy state, and later the electrons are relaxing, emitting a photon to the ground state. So as you probably know from the Boltzmann distribution, the Stokes-Raman scattering component is more intensive because we start from the uh, ground state, and the ground state is more dense populated than the excited states. Okay, Raman modes were assigned of the ODT passivated layer on the semiconductor surface were assigned on the basis of the previously done density functional theory calculations, and the observed Raman modes and experimental and DFT uh, calculations are listed here. And the most important modes that we will get into consideration will be the modes that corresponds to the sulfur hydrogen or even sulfur including groups like sulfur hydrogen stretching mode occurring at 2720 reciprocal centimeters will be one of the most important, because if you can see, you will see on the next slides that if we observe that the mode is the intensity of the mode is getting quicker, the passivated layer will soon start to disappear from the surface. And first carried out measurements by us was Raman spectroscopy aging measurements. And first, after the electrochemical passivation, the Raman spectra were recorded on a fresh new sample, which is on the bottom of the graph. And after that, we have stored a sample in lab conditions without access to light at room temperature, which means 22 degrees centigrade. And as you can see from the bottom to the top, after 1 month, after 2 months, and after even 6 months, the passivated layer became stable, and all visible Raman modes were also visible after a selected period of time. So the Raman spectroscopy aging measurements confirmed long-term stability of the passivated fuel layer. And what I noted is that important thing that differences in the band intensities and the nature of the background intensity is a matter of individual measurement, because Raman spectroscopy is mm, to say the character of a single measurement is really determined where you measure it. So a single, um, like going 5, for example, micrometers from the point that we measured seconds ago, can give you slightly different spectra than it was 5 micrometers to the right, to the left. Also, Raman spectroscopy measurements at low and high temperatures were made, and as you can see on the plot, low temperature stability measurements were performed in range between 100 and 300 kelvins, with different steps between the measurements, like 50, 25 kelvins. And as you can see, our recorded spectra confirm that the passivated layer is stable even at low temperatures reaching 100 kelvins, because as you can see, the modes were assigned and they are visible. So also the weak but the sulfur hydrogen group, which I mentioned earlier, is also visible. And like I said, obtained results validated the low temperature stability of ODT layers. And also it gave us information that there is no effect of low ambient temperatures on the passivation surface. So that's quite important for us. And also Raman spectroscopy measurements at high temperatures were made. Raman spectroscopy measures at high temperatures revealed the boundary temperature, whereby the fuel layer has disappeared from the surface. As you can see, we are starting from 295 kelvins, and we are going up to even 340 kelvins, which is on the top of all of these spectra. We are starting from lower to the higher temperature, from bottom to the top. And as you can see, with the increase in temperature, maybe not, you don't see it now, but I will show you later on the slide. the peaks of selected Raman bands are shifting towards lower wave number values, and I will explain why. And also the full width and half maximum of selected bands are getting broader. Uh, like I said earlier, the measurements carried out helped us to uh, detect the boundary temperature at which thiol layer disappeared from the semiconductor surface. It was about 335 kelvins, which is equal to about 62 degrees centigrade. And as you can see visually on the spectra at 330 kelvins, we still, that's the purple spectra, we still have the Raman modes of the ODT. And in 340 kelvins, we have no modes. So we can assume that the passivated layer has disappeared from the surface. The passivated layers of superlattice will found its application in infrared photodetectors and focal plane arrays. It's not that good because 62 degrees centigrade, where the thiol disappeared from the surface, is not that good for the application infrared photodetectors. But further research should be conducted because we have only now we have only made research on the gallium antimode with passivated with ODT layers, and we also should think maybe let's apply other thiols or uh, other thiols. And okay, and proceed to the last slide. Like I said earlier, the temperature evolution of selected Raman bands of peak center position and full width and half maximums were done. So as you can see, on different types of Raman modes like stretching, twisting, scissoring, and stretching vibrations of CH, CH2, CS groups were done. And as you can see with the increase in temperature, the centers of selected Raman bands are shifting towards lower wave number values because the higher temperature, the higher interatomic distances, the force constants between uh, single bonds are getting weaker, and so force constants are weaker. That means lower frequency, lower energy. So the wave numbers are shifting towards lower wave number values. And Raman, we say that Raman modes are uh, red shifting. And of course, with the temperature increase, the full width at half maximum increases. And I think that's all. Thank you for your attention. And if someone has any questions, I would very gentle ask. I would answer for them.
All right. Thank you very much. Comments, questions? Yeah.
So could you describe like which laser, which kind of laser you would use for your runs for experiments, like diamond type, for example,
Mhm. Thank you for a very good question. And these measurements were carried out using the argon laser with an excitation wavelength of 514.5 nanometers, and mostly because of the uh, organic character of thiol layers, we mostly use the lasers that have slightly uh, higher wavelengths because we don't want to excite the luminescence. We want to only see the Raman modes because the generally speaking luminescence phenomenon is several magnitudes greater in intensity than Raman modes. So we always try to use for these organic compounds like uh, lasers that have um, longer wavelengths. So, for example, 214.5 or even 785 nanometers for a semiconductor laser, because we don't want to excite a luminescence process, because, like I said before, luminescence process is several times in magnitude greater than Raman scattering process in intensity.
is this laser like pulse laser or it's like continuous wavelength? Would it somehow have some impact on your experiment, like the duration of the pulse, let's say, or energy of the
Uh, Generally speaking, the power output of the laser is modulated to have a good value, like a good value that also if you increase the power of the laser, you increase the intensity of visible modes. So if we are sure that the selected wavelength will not induce the luminescence, we can also apply more power, but we need to have in mind that we are recording spectra of an organic compound. So too much power in output of a laser could destroy it. So we need to have it in mind. Thank you very much.
Thank you. Thanks much again. And I will ask another next speaker. Be online. Yeah. Who will talk about new horizons in radon's prediction? Cryptic title.
I think that this is totally different
Okay,
topic.
that's good. We have some variation in the topics, and the floor is yours. Let's go. Yeah.
Is this possible to turn off those slides because they distract like visibility of this presentation?
But I don't know if it's not affecting the stream.
I mean that light,
What slide?
that over the presentation.
Oh, the lamp, the lights. Oh, yeah, yeah. Yep. Is that better? All right.
So welcome everyone in my presentation, and today I will talk about new horizon in radon prediction. And my name is Joanna Kubiak, and first I will tell you why I'm here and now with radon. So I finished my first degree in the University of Science and Technology in Krakow, and the technical physics, and there I meet some scientists that give me told me about the universe of radioactivity. But I feel sick to calling the Vor at Pole, so I come back to my hometown, and I choose the field environmental engineering. So, in environment engineering, I meet my supervision of master of thesis and doctoral thesis, and she's really amazing person, and she's doing uh, indoor air quality research. And I told she about radon, and she thought that this is good idea to add this parameter to her research. So this is the new chapter of the radon in the Poznan. And now I'm doing the doctoral school, and I do the research connection with the radon. And of course, I have still contact with the Krakow, and this is good because for example, Institute of the Nuclear Physics, we could find some radon masters. So the plan for today is the first short about environment engineering, next about radon, and about my research, and yeah, and this last but not least about research that will be during this yeah, and about environment engineering. Environmental engineering is some interdisciplinary field, and it is connection, and an environment engineer have to investigate the pollution, and it and the task of this environmental engineer is to prevent and do some research with this pollution. But of course, the pollution is connecting with the society too, because when people don't have knowledge about something, it is most dangerous for them. Uh, so this is reason why I'm doing radon research, because it could be to some hazard parameters. And it all started with the minerals. And uh, there, the minerals are um, that's from the really mysterious and strange disease. And the people can say that this is caused by legendary gnomes. But now we know that this is not gnomes, this is radon. And more described, this is radon dodgers. And I know that you, you, and you too, we all breathe now radioactivity radon because it is natural component of the eye, and it is the second cause of lung cancer, and it like to accumulate in the body. And what are the trends? 2 years ago, I want to search some topic for my doctoral thesis, and I read approximately 400 articles about radon, and more of them are about building. And a long part of these articles are about prediction of radon. And I find two some way of the prediction, and the most popular is machine learning, of course, and CFD simulation, and I choose the machine learning way. And now about my research. Uh, First, my research is about outdoor radon and connection with the Bundali layer, and I found that radon could be the good marker uh, of this some phenomenon. And the second is the second result is that radon measurements could be the have the long normal distribution. And next research is about radon in the nurseries, and I find that and other building, and I find that the radon concentration, radon profiles is really connection with the user's uh, profile. And the next, it I uh, I find that the active methods is better for the public building for the radon measurements than the passive methods. And I find that some outdoor parameters uh, could be compared with the indoor radon. And now I am doing the study that is connection with machine learning, and I find that radon measurements could be uh, divided by three periods, and this and I investigate that and assessment that uh, short radon measurements could be the good assessment for long-term radon measurements, and it is two good good results for us because it is only it is good measure radon only week to have some information that this building is good or not about radon, of course. And I doing, as I said, the environment engineering is connection with the society too. So I want to find how good is knowledge about ionization radiation in the Poland, and I want to, and I give some questionnaire, and I now I know that this knowledge is really bad. Yeah. And at the end, some words about radioactivity, and of course, the radon measurements in the future because we still have a lot of gaps in the lab of radon, and the lab is still changing. And I have some proposition. If you have some group of students, or if you want to test, uh, you can uh, do some questionnaire about ionization radiation, and uh, this is for free. This is good price for free to test your house. Uh, how high is your radon concentration in your room or uh, in your room where you working? And thank you for your attention. And yeah.
Thank you very much. Okay, this was a bit scary because it reminds me of like asbestos. So now we have to start worrying about radon and extract it from our house, the roofs and the walls and whatever. All right. Are there any questions? I think you should hand the service here and just,
If I can, but I can do this Polish. This
just ask if you want to fill it in. You should
do you want to do it or my question? Yeah.
so come up to
Oh,
one second. And then if you have time,
Yeah,
you have question, you can ask.
yeah. Two questions, two very short questions. Am I right that the increased concentration of radon is regional every?
This every but in the, for example, next to the crack, it is more rather concentration because the ground is has more radium, and radium is parent for the radon.
Okay. And the second question, because you studied 100 articles about the radon and so on, are there some artificial how to reduce the amount of radon to the air?
Yeah, in the thing, it is some no, how to say, but it's thing, some thick some when you have thick, when you're using has really good thickness, could be really bad for the rat because it could accumulate. So it is good to make less to less thickness and do the mechanical ventilation because the radon have a wall.
so does it come off the walls? Does it dissolve out the material? Or is it just going from the air?
Most of them are from the ground. It's because the radon that it's current. The radon is in the ground, but the materials we have uranium decay, so it is too, but the ground is more. And the basement is the first floor is the most radon.
Right. Yeah. People don't think about that daily, right? Okay. So I'll speaker, because you to the stage, we'll talk about all the our experimental setup, temperature control, and all the experiments.
So, good evening, ladies and gentlemen. My name is Jerzy Spakowski, and I am a student at Poznań University of Technology. And today I would like you to introduce you to the topic of temperature control in ODMR experimental setup. I will start by giving you introduction and theoretical background to the topic, as well as our motivation for conducting this research. I will show you an experimental setup and results obtained from it, and at the end I will present conclusions and used references. Starting from the very beginning, ODMR, or this stands for optically detected magnetic resonance, and it's a technique that is used to detect change, to detect magnetic, to measure magnetic resonance by detecting the changes in fluorescence intensity. As a sample that is a source of the emitted fluorescence, we are using microdiamonds with N4- color centers, which are shown in the photograph here in the form of a powder. And the crystal structure of them is shown here. We have a standard crystal structure of a diamond with carbon atoms, in which two adjacent atoms have been substituted with a nitrogen atom and a vacancy. And this structure, the nitrogen atom and vacancy, is called a color center, because that's this part of a diamond crystal is what gives diamonds
the color. In case of the particular sample, it is the fluorescence is in the color. It's in the red color in the range of 630 nanometers. Uh, here is here is a simplified diagram of the energy structure, energy level structure of the N4 minus center. There are a few keynotes, highlights worth keeping in mind. Firstly, both ground and excited levels are containing the one level corresponding to the spin quantum number equal to 0, and a pair of degenerate levels corresponding to the speed value of spin quantum number equal to plus or minus 1. The degeneration of this level splits in the presence of the external magnetic field, which is called the Zeeman effect. But in this particular conference, we are not concerned about this kind of fields. So we are only observing the effects of the zero field splitting of these states. The value of the difference of energies between levels corresponding to the value of ms to 0 or plus minus 1 is approximately 2.87 gigahertz in room temperature, which is in the range of microwave frequencies. So by applying the microwave frequencies and changing their value and tuning them, we can manipulate the occupation of these states with very high precision. Second thing, mm, both transitions from the triplet ground state and excited states, both excitation by laser, which is highlighted here by the green arrow, and relaxation, call, um, tends to conserve the value of the spin quantum number. So the excitation from the spin quantum number equal to 0 tends to stay at 0, and from plus minus 1 stays at plus minus 1. And the third thing is that the relaxation from the excited states corresponding to the value of 0 occurs via fluorescence, which is depicted here by the red arrow. And relaxation from the states corresponding to the value of plus minus 1 occurs via non-radiative intersystem transmissions. And combining these three facts, we can observe that by measuring the fluorescence, by inducing the fluorescence, inducing from the exciting sample to the excited state, and measuring the fluorescence by measuring the intensity of the fluorescence by applying the microwave frequencies, we can detect this occupation of the state by simply measuring the intensity of the fluorescence by changing the occupation and the type of relaxation that occurs in these centers. And as for the motivation for this research, as previously stated, the signal, the result, the fluorescence we are observing, is dependent on the external factors, like previously said, the magnetic field changes the energy structure. As also the external temperature causes the shift of the resonant frequency between the values of the energy levels. And this has a potential application as a very precise thermometer, because the resolution of the given ODMR signal can be very high and can potentially be used in very precise, for example, organic temperature measurements. Also, our experimental setup can be always extended towards measuring other samples, and given the knowledge and experience from working on this sample and working on this experimental setup can help us working in the future on some new other samples. And speaking about experimental setup, here is our homemade confocal microscope that is used to detect and measure the ODMR signal. Starting from the beginning, we have a laser light that's delivered by fiber optic cable. The laser light is being reflected from the dichroic mirror and forward towards the sample of the microdiamonds, which are placed on the microwave antenna with an external heater below. The laser induces the fluorescence, and the fluorescence depicted by the red arrow transitions through the dichroic mirror, the long pass filter, and the spatial filter, and is being reflected and transmitted through beam splitter towards CCD camera and a photo detector.
The entire diagram, entire experimental setup, including the main hardware used for this experiment, is shown right here. Mainly, we have a 520 nanometer diode laser that is used as a source of the laser light, inducing the fluorescence. The laser light traveling through the confocal microscope is being collected by the photodetector, and the ODMR signal from the photodetector is being passed through the lock-in amplifier, which is a device that is used to amplify the signal from the noise, because the raw signal from the photodetector can be very noisy and very hard to analyze, and the signal after the amplification using the lock-in method can be much smoother and much more precise, and with much higher resolution. After being converted from analog to digital, the entire signal is collected by the Raspberry Pi board, which is simultaneously sets parameters of the microwave synthesizer for each step of the detection by photodetector. And since amplification using clock-in method requires modulation, we are using a modulator for the microwave uh, with a built-in function in the lock-in amplifier. And here is the example of the one of the example of the ODMR signal and how to analyze it. First of all, I said that by mm, applying the microwave around the microwave frequency, we can see that the difference in fluorescent intensity, and we should be seeing the decrease of the fluorescence intensity. As you can see here, it looks like we are seeing the increase of the fluorescence intensity, but it's actually quite deceiving because the signal is not coming through the photodetector but through the lock-in amplifier, and this phenomenon of flipping the signal upside down is because of the amplification using lock-in method. So down here below we have a high fluorescence, and over here it is lower fluorescence. That's why um, that's because the axis is upside down. I mean, should be thought of as being upside down. Uh, and to compare and analyze and measure these ODMR signals, we are fitting function. We are fitting the double pseudo-Foid function to these signals. Uh, the function is presented here. And the entire function has two components, each corresponding to each of the dips, and each component has two profiles: the Lorentzian profile and the Gaussian profile, that is with scaling factor in between them to allow us better precision of fitting and better analysis of the signal. And the main components of this function and main components of this ODMR signal are the resonant frequency, and labeled as me 0, the full width at half value, uh, depicted by gamma 1 2, and the splitting of the dips depicted as a gamma. And this by comparing this mainly comparing the resonant frequency and the delta split, we can compare two different signals or a set of signals. Like I previously said, maybe in the case of magnetic fields, we are observing the splitting of the energy levels, and each of the dips fluorescence corresponds to the energy level, one of the energy levels. And by applying external magnetic field, we are observing the higher value of splitting visible in the other signal, splitting corresponding to the energy levels. In the case of increasing temperature, we are observing the shifting of the resonant frequency value, which is depicted in the over here. We have two ODMR signals, one collected at 307 Kelvin, depicted in purple, and the other one collected at 345 Kelvin, depicted in green. The black dashed line shows the theoretical resonant frequency at room temperature of precisely 2.87 gigahertz, and the red lines show the resonant frequency of the signal collected in first in 307 Kelvin and 345 Kelvin,
and we can visibly see the shift between the values, which is measurable, and in this particular case, it was 0.26 gigahertz. This particular set of measurements were performed using low laser power, which causes the value of the overall intensity of the fluorescence to be quite lower. That's why the signal is quite noisy compared to the first one I showed. But still, uh, even with low levels of fluorescence intensity, the 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 shift of the resonant frequency is still visible and easily measurable. And to wrap things up, as a conclusion, in this particular research, a experimental setup used to detect and measure ODMR signal in the presence of external temperature was shown, resonant and shifting of resonant frequency in relation to temperature was shown. As for future plans for this research, we are working on constructing a slightly better, I mean, just better confocal microscope depicted here as a model in AutoCAD. We are working on providing a cooling system that will allow us to measure temperatures of the immersive in temperatures in lower temperatures than room temperature, and also trying to perform measurements of with greater resolution in smaller range of temperatures, which can have, as I said previously, can have potential applications as a precise thermometer, uh, very specific range of temperatures. And other samples, mainly nitrate, hexagonal nitrate boron, gallium nitrate, are possible new materials that will be able to depict it, to be measured in this experimental setup. So that concludes my speech. Thank you very much for your attention. If you have any questions, feel free to ask them.
Right, thank you very much. All right, question.
I have one question. You said that this can be used in very precise temperature measurement. Well, this is quite advanced device, and in which type of situation we can use them to measure temperature instead of other simpler devices.
Okay, so
So first of all, our experimental setup currently doesn't allow the measurement of the ODMR signal in real time, but I have seen other experimental setups that allow that. We can see because the signal I shown was the result of averaging, like I believe 400, each point was an average of 400 different samples, 400 different measurements, which can take some time from like few minutes to like maybe even 30 minutes or longer. But it is possible to make a OMR's experimental setup that shows you these signals in real time. And first of all, it is possible to increase because it is so precise, because we are operating in a range of microwaves, which is like compared to, let's say, visible light. Visible light is in nanometers, and it's like 10 to the, I don't remember, very high power of hertz. And we have gigahertz here, which is 10 to the power of 9, which is much smaller. So we have much greater resolution. So the potential application of that is that even though it may be harder to just measure the temperature of a sample, it can provide you with much greater precision and much greater resolution of given temperature.
Anyone else? Can I have one?
Yep.
So where you show the shift of the ODMR signal as a function of temperature, I assume that this temperature was given, this was the ambient temperature or the heating of the entire sample. But when you have interaction of your diamond nanocrystals, microcrystals with the microwave frequency, so the interaction, the fact that you apply microwave frequency also raises the temperature of the nanocrystal. So the question is that included here is the quantum score. So if you apply 307 Kelvin, is it 307? Is it the 307 that you apply, but it's actually 310 because of the microwave?
Okay, so it actually depends. I mean, this can
particular case, the samples we're measuring for this are, let's say, not the greatest possible quality. They're not pure, as pure as they could be. That's why, for example, in this graph, you can see that the signal is noisy because we have to use low laser power, not to laser hit the samples. But we also tested with some very pure samples that have many very few imperfections, and we observed that in that case, there's basically the effects of laser heating are very barely noticeable. So first of all, the dependence of the temperature from both laser and microwaves is dependent on the sample itself. Some samples heat up more, some samples heat up less. In this case, the applied temperature was the shown temperature here was the temperature set on the heater because of our current capacities of precise temperature measurement were just not sufficient enough to help this.
Okay. If there are no other questions, then let's thank Jerzy once again. Now we'll thank one last speaker, which is Agnieszka, and she will talk about lipid membrane and how one can measure orientation of molecules in lipid membrane.
Hello everyone, I'm Alestin and today I want to tell you about how to measure the orientation of molecules in lipid membrane. So firstly, to start, I want to tell a few words about lipid membrane. Generally, the cell membrane is composed of lipids, proteins, cholesterol, and the lipid structure and the reactions to the drive separation process. Unsaturated lipids compose the liquid disordered phase, in which there are regions enriched with saturated lipids like sphingomyelin and cholesterol. And generally, orientation of different molecules such as proteins and environmental sensitive probes influence their behavior and physical their behavior and properties, and even impact their uh, and even impact their proper functioning. Generally, to examine the cell membrane, scientists use simplified models, and in my research, I decided to use the supported lipid bilayer model because it imitates well the native structure of the membrane. And to prepare such a membrane, I started with lipid vesicles, which rupture spontaneously in contact with solid support, and it's formed a lipid bilayer. And my bilayer has two phases: liquid ordered phase composed of sphingomyelin and cholesterol, and liquid disordered phase composed of phosphocholine. And examine the membrane, I'm using fluorescence microscopy, and of course we have here some fluorescence dyes to use this technique. And I decided to use Laurel molecules because it's distributed evenly in the whole membrane regardless of the lipid phase, and its spectra depends on polarity of the immediate environment. Moreover, the recent results of molecular dynamic simulations showed that these molecules can take different orientation, which determine the transition development of the molecule. So I can check the orientation. I'd like to check this orientation of these molecules in the membrane. And how to do this? I decided to use azimutally and rotary polarized beams. And by exciting molecules with these beams and analyzing fluorescent images, I could extract information about the orientation of these molecules. What is special about these beams? They have different special components of electromagnetic field intensity. Azimuthal beam has this electric field component only in the plane, while the beam has out of plane component. So it means that by exciting molecules with this azimuthal beam, I will excite efficient molecules which are oriented more in the focal plane, but with the radial beam, I could extract information also about molecules with transition dipole moment oriented more out of the plane. And here you can see my results. Here are two images of the membrane. These darker spots are liquid ordered phase, and the green part is liquid disordered phase. And I always image the same area of the membrane with azymutally and with radially polarized beam. So I compare the same area. And here, as you can see, for the excitation for radially polarized beam, the contrast between the liquid ordered and liquid disordered phase is lower. So it means that here in the liquid ordered phase, so it is darker in the liquid ordered phase, so it's in darker spots. The molecules of laudan are oriented more towards the lipid tails. And to quantify these values, I decided to calculate the ratio of fluorescent intensity obtained by excitation molecules in azymutally by exciting these molecules azymutally polarized to fluorescence intensity obtained for molecules exciting by radially polarized beams in each phase. So separately for a liquid ordered and for liquid disordered phase. Then I compared these experimental results with theoretical results. So I calculated it theoretically, and here you can see these experimental values and the cross point between this theoretical value and experimental values corresponds uh, to, to the average temperature that allowed us created in the membrane, liquid ordered phase, and in ordered phase amounts to around 33 degrees, and liquid disordered phase it's around 41 degrees. Such level orientation can be explained by different lipid packing. So in liquid ordered phase, are more packed, so these molecules have to be oriented more towards the lipid states, while in the ordered phase, molecules have more space to be oriented in the focal plane. So during my research, I showed that I can use highly and radicalized beams to measure the orientation of the molecules in the lipid membrane, and moreover, I calculated the power orientation of laudan in liquid ordered and liquid disordered phase. Thank you for your attention.
Thank you very much, Agnieszka. Questions, comments, doubts? Okay, so I have one. If you can go back to your the theoretical calculation, okay? So this is an average angle, right?
Yes.
About the distribution. So are all the molecules oriented exactly the same way, or you would expect that there are thousands of molecules that be oriented slightly differently?
Generally, I see that also with the simulations on this paper with simulations, they are rated, slightly different, not every each the same. And generally, I'd like to check single molecules orientation, but in the future, because it's rather more complicated task, I started with this one to check if I can measure it, and then I will try to measure single molecules.
Okay, then you'll have to go one by one.
Yes, exactly.
All right. No other questions? Then let's thank Agnieszka again. Now, the last speaker, Mr. Piotr Radomski, who will talk about a lot of different metal nucleosides, hybrid systems, and I guess the applicability of these systems. Well, I can already see it. You're theoretical stuff.
Exactly. Okay, so thank you for the kind introduction. And I try to be quick because I have to be the last one for the land. So without my name is Piotr. I'm a second student here at the Poznań University of Technology, and my talk is going to be about the impact of transition metal versus the carbon atom on the absorption of nitrogen oxides on the middle layers of transition metal decalculations, MOS2, C2, and WS2. So we have an excellent presentation about the radon. I will speak more. We have other pollutants, and for example, I think World Health Organization 2019 99% of the population, including Poland, lived in the areas where air quality guidelines were definitely not met. Hence, we are need efficient and reliable sensors and materials to deal with this problem. And excellent materials for this purpose are the monolayers of chemical coordinates, in short. This is because they exhibit excellent sensitivity to many dangerous gases. For example, they can detect nitrogen dioxide at concentration of single part per billion, not per million, per billion. And also these effects are selective and they can operate at room temperature in weak undergas conditions, which is unlike many conductor sensors which have to be up to several hundred degrees Celsius to operate efficiently. And here you can see the basic structure of hexagonal TMB with orange atom symbolizing the carbon atom and the blue one is the transition metal. And the aim of our talk is to answer the question which of these atoms has the is more important with respect to the absorption, the carbon atom or the transition metal atom. So we compare three specific TMBs which differ by these selected atoms. And as all theoretical work start, I will also start with many questions and tests. Then we proceed to create 10 distinct formations which allowed us sufficiently draw the space of possible outcomes. And then we ask for the systems and proceed to calculate the unit properties. All of the calculations were employed, the calculations employed the quantum expressive density functional theory package. And this, here you can see the parameters. I won't go through all of them on Google. However, I want to emphasize the importance of the dipole correction layer, which is necessary when you are calculating the absorption of two-dimensional material in periodic boundary conditions, and also Green's Green method, which allows us to properly treat the van der Waals forces. So two fundamental parameters by which we can judge the absorption energy defined here as the difference between the energy of the system and energy of free molecules and free layers. And the charge transfer is defined as the difference between the charge of a certain molecule and free molecule. Let's get to the results. Here you can see the relaxed concentrations. And what I want to note from the slide is that all of this seems pretty similar. So, for example, we do not have chemical bonding, and all of the molecules are undefolded. However, if you plot the absorption energy and also charge transfers, you can see some trends. So, for example, the nitrogen dioxide interacts the most, and to better appreciate these trends, you can plot the average values. So here, you can see on the left side that we have some average values for different materials, and nitrogen dioxide reacts to the type of this material much more than the other molecules, because the lines are pretty flat in their cases. And to better appreciate which atom is more important in this absorption, here we have difference between these three TMDs, and we can see it is visible that the change of carbon atom is much more important. The difference is much larger than in the case of swapping the transition method. And this is especially visible for nitrogen dioxide. For nitrogen oxide, we have similar effect, but much more diminished. And for nitrogen, do not offset such effects. So if you detect explanation of this effect, I encourage you to check our previous work. However, long story short, the reason that strength of bonding with the metal atom, so the stronger the bond, the less charge is available above the surface of the material, and the more charge is available, the molecule can take it, and we have stronger absorption. However, not all of the species can benefit from it, because the molecule has also to be a good acceptor. And for example, if you have nitrogen dioxide, really good acceptor, it will benefit from this effect. The absorption will be enhanced, but not as much in case of other investigated specimens. Perfect. Stop working. Okay. So as we also wanted the experimental tests to benefit from our work, we calculated some average changes in charge concentrations using Langmuir absorption model, and using these values you can predict the impact of the absorption on the resistance of your material. And you can, for example, compare the different resistance results on few different monolayers of PNP and create very sensitive, very sensitive sensor. So, sum up, we've shown MOS2 is the most responsive to nitrogen oxides, followed by WS and then MOS2. Also, the carbon atom has significantly more impact than the transition metal atom. And as I said before, the more benefit from this effect, the molecule has to be a good charge acceptor. So, ladies and gentlemen, thank you for your attention. I also want to thank Dr. Maciej Szary, who is the co-author of the original paper and who's the main originator of the idea for this work. And I want to thank the Ministry of Science and Education in Poland and Poznań Supercomputing and Networking Center for their support. Thank you very much and have a nice night.
Thank you. All right. Before we head off for some food, I'm sure everybody's hungry already, but any questions? All right, please go ahead.
Do you plan an experiment on this one?
It would be very nice when we are a group of we doing theoretical work. So I look forward to some cooperation with experimental chemists and physicists. However, now we timber and of course extremely material because with effects and with many layers, it is a different story. There were some other effects we are currently investigating, and then you have to like scale the response of the system with the known amount of gas in the chamber, and you will measure the resistance of the layer.
But I would go more towards, are you planning to have it as like a single layer in a transistor? Or are you thinking about like a printed thin film thing?
The most optimal solution, because you have to remember our calculators are in perfect vacuum and 0 Kelvin, which is unachievable in real life. So I think the most optimal solution would be to have a quasi three layer, for example, on like the hydrogen we collected between the layer and the other material, like mica or something. But I don't know if that would work exactly as calculated. I hope so. I can only hope so.
Yeah, because your calculations will definitely need to be correlated with the design of experiments. Because depending on how you design it, there are specific things which you need to take into consideration. For example, if you have a thin film of individual layers, you will need also to take into account junction, let's say, what will happen on the sides and so on. So it will be a fun thing to do. I will put it this way.
I hope something.
No, I mean interesting.
Yeah,
I want to say interesting.
Thank you for your question.
Yeah, as an experimentalist myself, I see only problems in going to the experiment. So, well, it's obviously, so you motivated. I'm going to stir a little bit of controversy before we go for a break, but you motivated it as potential sensor with all its benefits for pollutants, right? And now one comment is, okay, so theoretically you tested it on very simple molecules and pure molecules, right? If I want to use this as a sensor, first of all, it's exposed to ambient conditions. Second of all, it's exposed to a mixture of all kinds of gases. So how not sensitive, but how specific would be the response of your sensor to a specific pollutant, right? And all these kind of questions come to play now.
Okay, so we also know that it is pretty next to the oxygen, and we know from this work that it is next to the nitrogen. So we have that like with the most component of the atmosphere, and also I wasn't talking about this, but this work is based on the experimental work that previously have shown that this sensor indeed works. So this is not like our idea from the beginning, but it's motivated by this experiment.
Sure.
And also, of course, you can if you have a mixture of gases, this is the advantage of materials because we have different answers to different gases, and by comparing these gases, we can analyze not only the single component but also all of the components from the mixture. And but this one is not other components. So
Okay, that would be
I was going to
Yeah.
nice. Thank you for it.
all right. So let's thank all the speakers of this session. Joining me now. So we went through a bunch of different topics. We had magnetic fields, we had cell memories, we had metals, but not. So I think it's very insightful and very refreshing to everybody. So let's go for lunch now. It's downstairs, and then the lunch break will take place until 2:30. So 2:30 the session
University of Technology. So that.
Thank you. Okay. Right. So first of all, thank you very much to the organizers for having me here. It's always a pleasure to be at Poznan University of Technology. Today, I would like to tell you a little bit about one project only, but which has been running around for several years now, which took a lot of experimental and modeling resources, and is actually running across the ocean because we have collaborators from Los Alamos National Laboratory, from Air Force Research Lab, and from UK, from Germany, and from Spain actually, and from Poland. So it's quite a vast amount of energy went into this project. And to start with, because I think there are people from different areas, so I unfortunately will have to start from very basics. So sorry if someone is very familiar with that. Today I will be talking about carbon nanotubes, and probably every one of you have heard about graphene. Graphene is a structure which you can imagine as a flat layer of carbon atoms arranged in a hexagonal lattice. And if you form a nanotube out of this one, you just need to roll it up. Obviously, no one sits in the lab and rolls them up. We don't do that. We grow this on catalysts. For example, a piece of a nanocatalyst of iron. And so these are the nanotubes. And why scientists got interested in them? Firstly, because they are very conductive structures. They are characterized with ballistic conduction. They are stronger than steel. They are more thermal conductive or similarly conductive thermally to diamond. They lack skin effect. They are more lightweight than aluminum, and they are chemically resistant, very inexpensive. They can be produced out of greenhouse gases. And if you think about it, this means a lot of interesting applications for them. But one of them, which has been around for years now, is to make them into electrical wires, because all these properties make ideal candidates for electrical wires. And I know it's electrical wire is a very hidden component of many things, but if you think about all electricity that we are using, you will know that we use a lot of electrical wires. To give you one example, such a plane using 2 tons of copper wiring. And let's imagine we cut this amount by this way half. Obviously, you can take less fuel, you can take more luggage, and it's really a very good saving. So actually, having such interesting wires would be amazing. But how to turn an individual nanotube into a wire? It's a little bit of a problem because we have to move from nano to a macro scale. So what people discovered is that carbon nanotubes are very happily sticking together during and in some processing. So if you put many nanotubes together, what you can do is form a fiber. You can imagine such a fiber as a cotton thread, cotton yarn, made fully of nanotubes. So we assume that these nanotubes are aligned along the fiber, and these fibers are mainly made of only 19% made of nanotubes. And this is an example of a process that I have been working with during my PhD. One of the processes of making such smooth fibers. So what we have here is a CVD reactor with temperatures about 1,000 degrees. We introduce some carbon source like methane, a little bit of iron catalyst in the form of ferrocene and sulfur source. In the hot zone of the reactor, we are forming carbon nanotubes. We are growing them, and they are forming an elastic cloud, which at the bottom of the reactor can be extracted by a metal rod. And because of the thermal differences, they are actually sticking nicely to the rod, and these nanotubes are sticking to each other. Once you have the film of nanotubes out, what you can do is to spray acetone on it, and by capillary forces, when the acetone is evaporating, it's actually collapsing the nanotubes into a unit of fiber, and then you put them on a bobbin. So this is how you produce kilometers of these fibers in quite a simple fashion. But the problem with these nanotubes at the moment is that these fibers are extremely strong at the moment, but not as conductive as we would like them to be. And there are several reasons for that. The first reason is that actually the nanotube is not, every nanotube is not the same. Actually, depending on how you roll up the graphene layer, you may obtain metals, maybe semi-metals, and a number of semiconductors. And if you think about it, there are probably up to 200 types of chiralities which we may expect. Also, what you can have is a single walled nanotube, double walled nanotube, and triple walled nanotube, and multi-walled nanotubes. And actually, the best are single walled nanotubes, and the best would be to have metallic nanotubes. But up to now, we don't have really selectivity in the processes that we have. What is more, do the practical fibers, you will obtain different types of nanotubes of different lengths. You may have varying alignment. You can see it here actually, but the alignment of nanotubes is not ideal. You may have problems with densification of these structures, some lattice defects, doping problems, impurities, and many more things which are actually playing a role in terms of electrical conduction. So obviously, the first thing that people have been doing is to study these things experimentally, and they improved a lot from the time I started working on it. The second thing is that theoreticians try to foresee what will happen if we have how would the ideal structure of a fiber look like. But also the second part of these studies is that they take different types of CNT fibers from different processes, and they try to analyze what are the transport models and transport properties of these fibers. For that, what they do is that they test the resistance in terms of temperature, and also they check what is the change of resistance of these fibers in magnetic fields. And based on that, there is a range of models which have been developed in 1990s, long back, and even 1980s, which have been developed for conductive polymers. And they are trying, and these models have nice equations, and they are trying to fit these models into the data. And there is a long-going debate. There is a long-going debate about how to fit it properly, which one is working, which one is not working, and so on and so on. The second problem which appears here is that very often, especially if we go for magnetic fields, people are limited only to 10, maybe 12 Teslas. So very often we are missing a lot of data which would be useful for proper fitting. So, because I'm an experimentalist, the first thing which we decided with my colleague is to go for much higher fields. So that's why we went to Los Alamos National Labs, tested our materials in the fields up to 60 Tesla, which is, believe me, quite a bit. Uh, and and also we took several types of fibers because obviously we wanted to see differences. So this is all CVD method that I showed you before. So for example, we have an ethanol fiber, which is quite nice, but mostly having double walled nanotubes. Very clean. Then hexane, which was actually a dirty one with lots of multi-walled nanotubes, and also a methane fiber, which was having mostly single-walled nanotubes, prevailingly potentially metallic ones, but not all of them. We put them into the setup and blasted them with 60 Teslas, and we went down to temperature with them. And this is what we the type of data we obtained. We had the resistance versus temperature and magnetoresistance versus field. So which means the changes of resistance with the field and the temperature. This is example of the data that we obtained. And these are all 5 samples that we tested. And obviously, going with the art that we knew before, we started to feed the data. We analyzed that our data is probably well within the metallic region of MI transition. And so we started just to make sure we started to feed the data into 3D variable range hopping. As you can see, a red curve is not really fitting a black curve, so probably we can be sure that we are on the metallic side. Some of the data could fit into it, but not so well. So then we went to the weak localization models, which should be used when we are at the metallic side of MI transition. And we started to feed them. And as you can see, again, some of the data fits better, some of the data fits worse. There is a strong debate whether we should use these weak localization models or whether we should use the fluctuation-induced tunneling methods. And again, we did them. Some of them were not. And this is what made me really upset, because after a while you could fit an elephant. So this is the moment where I decided that I don't want to stick to the models that have been around for 30 years right now, but we should think about some new methodology. And this is where I started to work with theoretical modelers from Spain and from Poland as well, and from Germany. And what they started, they actually took all the models that they knew, and they added a component which is a magnetic field component that no one actually has done it so far. People were adding this component and testing only individual nanotubes, but what they did, they tested that for not only individual nanotubes, but also for several types of junctions of nanotubes with different chiralities. We did loops, we did doped nanotubes, and we also did defective nanotubes. And we even rotated the nanotubes just to see what are really kind of things which are responsible for the things we see. And what is very interesting is that up to this point, everyone was thinking that, for example, negative magnetoresistance is because of the weak localization only. But what we have found is also because of strong geometrical mismatch between chiralities. And this is actually not possible to see these things if you only fit data. The second thing is that, for example, if we have matching chiralities, the defects are playing the highest role. This is where you start to have negative magnetoresistance, and so on and so on. So, for example, the effect of doping, the effect of length of the of the nanotube. So, actually, when you see all this data, the moment we are covering the final results and trying to see the percentages actually of these effects, how they are affecting the whole structure. We are sure obviously that this is not showing you every possible effect that is there, but I think we cover most of them. And what is the most beautiful out of it is that you can apply it to graphene fibers, you can apply it to 2D materials, you can apply it to other 1D materials, and many, many more. So I believe this is like a good start for going further. And this is because we managed to kind of work with people who can do the changes into the Siesta code, and who could actually add the parameters of magnetic fields in different directions. So I think this is cool because it's developing several fields of studies. Thank you very much.
Thank you very much. Are there any questions for our speaker?
Yes, so these fibers are actually already in the market. They are a bit expensive at the moment. For example, in US, there is a company called Nanocom. They are producing these fibers commercially. But also there's lots of literature where if not having a single reactor, you can go for so-called wet spinning. And in such a case, you make a dispersion of nanotubes, and you have to coagulate this dispersion in solvent, and this is how you can produce these fibers in a slightly different way, but also I would say more accessible to more labs. It's possible.
And is it any possibility that you could share the some kind of literature of it to like to redevelop it further?
Yeah, I mean, it's
Let's
like,
use
yeah. If you, for example, the Google Scholar for itself, there is the first paper that is appearing there, which is a big review about the types of these fibers. Yep.
I would like to ask out of curiosity, I understand that actually process of production of nutrients that citrus, it's like producing sugar or cotton candy, like
Yeah. Some people kind of call it this way because it's like say it's a candy floss. I wouldn't say so. Because in the candy floss process, you just melt, and you do the chemical reaction to synthesize nanotubes first. But then, but after this, it's really that we have like a sticky cloud. I guess. Because all interactions, these nanotubes cluster very nicely together. So we want to stick together.
but they're running because of this mechanical, like because they're melted with these chemicals and they're mechanically like wrapped. It's some kind of chemical process that they are on
At the process of sticking to the metal rod, it's physical. It's no longer a chemical process. The chemical process is during the synthesis of the nanotubes. So first you have a synthesis of nanotubes, and then they stick together by van der Waals. So you have an
I mean,
yes.
like, what my question is, do they wrap, like, do they form the steel tubes mechanically or
chemically.
Are there another questions? Speaker? Okay. So thank you very much. We are very glad that you accepted our invitation. And our next speaker will continue the topic of carbon nanotubes. We have the floor is yours.
Okay, hello everyone. My topic of my presentation is also connected to nanotubes. Lucky for me, I still have something to say about it. Uh, so, uh, my topic is determination of CNTs and geometric parameters using UFOVC method. And of course, at the beginning, I have definition of carbon nanotubes, but a lot of things has been said about it. But as we can see, if we roll this graphene in different ways, we can obtain armchair, zigzag, or hero type of nanotube. We have single walled and multi-walled nanotubes, and some of these nanotubes have different properties. Excuse me. Uh, and as we can see, and nanotubes have electrical elastic potential in a lot of fields like molecular electronics. We can use them in member files,
conductive coating, humidity and gas sensors, uh, even in lithium-ion batteries and hydrogen storage. So we want to know their properties really well because we want to uh, use correct type of nanotube for our project. Uh, to describe our nanotubes, we are going to talk about UVV absorption but I'm going to talk about components of electron energy loss spectroscopy. So as we can see, we can decompose this spectrum into uh, IB electron transitions. Uh, in PE is a surface plasmon associated with p orbital, sp1 and sp2 associated with sigma and p orbitals. And P is a plasmon that propagates from a certain axis of carbon nanotubes to its surface are associated with the P and sigma plasmon orbitals. But we are using FOV's absorption because it's easier for us. Also, the peak shift can change because type of light polarization, for example, S-type polarization, do not cause change in our peak because all the time polarization is perpendicular to carbon nanotubes. But for P-type polarization, when we are changing the angle that we are emitting on the nanotubes, we can see that at the beginning they are parallel, and if we change our angle, they become perpendicular. So we can see that there is a shift towards lower energies and peak increased. Okay, we examined our nanotubes using transmission electron microscopy. As we can see, uh, uh, we uh, we checked inner and outer diameters of carbon nanotubes, multi-wall carbon nanotubes, and as we can see uh, in one type of nanotubes, we can obtain different diameters. Predominated diameter is lucky for us individual to uh, this type of nanotubes, as we can see. Uh, we also demonstrated our results in this table, and as we can see, producer tells us his own diameter, and as we can see, our examination shows that they are lying to us. Wow, shocking. Producer is talking that their product is perfect. Well, it's not. And as we can see, we checked how UV spectrum change when we are, for example, increasing our outer diameter, uh, when we are decreasing our wall thickness, and when there is more defects. As we can see, the peak shifts towards bigger wavelength, and when we are decreasing our diameter and increasing our wall uh, thickness, there is opposite result. We created our samples by uh, making a solution of carbon nanotubes and dichloromethan, and to eliminate influence of the solvent, uh, we deposited on this our solution on quartz substrates using dipping technique. The technique was chosen due to its simplicity and speed. As we can see, uh, for low speed, results are really inconsidered. So we choose dipping speed 20 millimeters per minute and drying time 10 seconds to evaporate solvent. And as we can see, of solvent cost, a small shift to our to 300 nanometers and a small amount of noise on our spectrum. Uh, our spectrum was decomposed into its components, and as we can see here, there are our results of these components depending on uh, nanotube properties like outer diameter. And when we collected our data earlier, results from uh, my coworkers, Dr. Rittel, and literature results from Dr. Graham, we can create this graph that shows how uh, maximal absorption energy change when we are changing our uh, outer diameter. So we can see that for single volt there is a decrease of energy when we are increasing our diameter, but for multi-volt carbon nanotubes, there is a sudden increase for something like 20 nanometers. We are still checking other numbers, other types of carbon nanotubes, and we will see how exactly this graph can look. This is just visualization what we already have, but not complete. So the paper determined the exact range of tested diameters and demonstrated the influence of carbon nanotube parameters of in the shift of the absorption maximum and spectral components. The dependence of the normalized absorption at 500 nanometer on the cross-sectional area of nanotubes for logarithmic scale was determined, and obtained results significantly extend the literature data and additionally enabled the demonstration of the trend in the change of absorption energy for various types of nanotubes. And this is, and for now, any questions? Just like I thought, listen, I'm listening.
I have actually a question. So, as I understand well, if you when you want to see the diameters of these nanotubes, you do EM.
Yes, exactly.
Would you think about having some more better methods to do that? Because I've heard about some methods where you can use AI, for example, recognize images of the nanotubes, and then but I've never had access to that.
Well, I tried to do this, but results are very poor because at the beginning I tried to check only one single nanotube, and every result it gives me was from this one particular nanotube. Uh, uh, I adapted one picture when there were exactly three nanotubes. Uh, one was, I don't know, it was defected, and two others had exactly like 15 nanometers, and was exactly 15 nanometers in this picture. So I did this all by myself. Uh,
It's tedious, very tedious, because you have the same problem when you synthesize nanotubes, and
we are also working on segregation method to segregate one type from another by simplification. We already have success in one example, but there is still too little data to say something more. Any other questions? Okay.
Thank you very much. It's good. So we can see that no matter where you do your studies with carbon nanotubes, the problems are the same. So it's good to see each other and tell about it. And our next speaker will be Andrzej Zakręcki. He's not here.
He's online.
He's online. Okay, I'm sorry. So
Yeah,
welcome, and
I'm here.
floor
Do
is
you
yours. The
do you
platform is
hear,
yours.
do you hear me? Hello, do you hear me? Okay, so let's start from my presentation. Today presentation aims to outline the importance of 3D printing technology.
Andrzej, can you hear us?
Yes, I am. Do you hear me?
We have some technical issues, but we are working on it.
Hello, do you hear me?
Could you say something?
Do you hear me? I'm here.
So we'll make some break because we need to find another technician who could solve this issue.
Do you hear me right now?
We gladly have a lot of time, so we don't have to hurry.
Hello? Hello, do you hear me?
No, we know that he's here, but we can't hear him. The support is coming, so I hope that this issue will be resolved soon.
Do you hear me right now?
was a music break.
That was a test. Could you please check if the speaker can we hear speaker?
Andrzej, can you hear us?
Yes, I hear everything.
Okay, and now we can also hear you gladly. Welcome, and you can start your presentation.
Okay, thank you. Let's start from the beginning. Today's presentation aims to outline the importance of 3D printing technology in implementing modern manufacturing methods for orthopedic supply. Using forearm injuries as an example, I will present the possibility of replacing traditional plaster cast with solution based on the 3D printing technology. Since we started the presentation, already 5 to 10 people in the world have suffered from the forearm injuries. Forearm injuries account for more than 70% of all injuries in the human body. The approximate number of the forearm injuries in the European Union is almost 3 million people per year. In Poland, there is about 250,000 injuries per year. The numbers continue to rise due to the aging population and increased fracture risk. Most commonly, the patient is placed in the conventional plaster cast for about 4 to 6 weeks. Although the traditional plaster cast effectively stiffens the fractured bone, it has many disadvantages. Firstly, it is pretty heavy, and its improper placement can lead to the numerous complications such as local maceration of the skin, necrosis due to the pressure, and nerve damage. Secondly, a plaster cast not only significantly limits of the movement of the affected limb, but also weakens the muscle tone when worn out for the long period. Awareness of modern treatment methods for forearm injuries is increasing, and alternatives are increasing being used instead of the classic white cast like um, orthosis. Research shows that materials used in the 3D printing technology, such as polyimide PL12, PETG, or ABS, make it possible to create functional orthoses with stiffness comparable to the traditional cast. However, to develop such as orthosis model, it is necessary to prepare an accurate 3D model of the forearm and select a suitable material and manufacturing technology. The choice of the material and manufacturing technology is a key factor in the design of the new solution. The choice of the material affects the wall thickness, strength, flexibility, minimum component size, manufacturing quality, and ease of certification of the new product. The technologies used were powder bed fusion, selective laser sintering with the polyimide PL2200 using in EOS P396 machine, and HP multi-jet fusion with polyimide PL12 using HP 5200 machine. The choice of these technologies and materials was dictated by biocompatibility. The parts made with the PBF technology using SLS and HP MGF methods were subjected to finishing, smoothing polishing using Dimension PowerShot C, polishing the Dimension PowerShot S, and coloring in the DM60 machine, polishing using Dimension PowerShot C, dyeing in DM60, and chemical smoothing in PowerFuse S. In the order to select the best solution and evaluation to the chosen material and manufacturing technology using the following methods: tensile testing to determine the tensile strength, modulus of elasticity and elongation at break, flexural testing to assess the bending strength, and impact strength to test material resistance to dynamic loads. These methods enable a comprehensive characterization of the material, providing key information on its material properties and behavior in potential application. The tensile strength and modulus of elasticity of the samples produced by SLS and MGF technologies are statistically compatible with the average tensile strength values at 43 megapascals and 42 megapascals respectively. The manufacturing technology affects elongation at break, where SLS samples showed significantly higher values in X and Y orientation. The orientation of the specimens affects all strength parameters tested, with differences due to the layered structure of the models. Specimens made using MGF method show the higher flexural strength of the approximately 5% compared to the SLS specimens with average values 66 megapascals and 61 megapascals. The flexural modulus of the MGF specimens was higher than SLS specimens, and the difference in the modulus and the strength values were due to the orientation of the specimens. The SLS specimens had higher repeatability parameters, indicating their more homogeneous material properties in the same orientation. The SLS specimens exhibited higher impact strength in the X and Y orientations, indicating their more significant anisotropy of the mechanical properties. The results shows that the MGF technology specimens had lower impact strength and less scatter, suggesting more homogeneous properties in the different orientation. The tensile test analysis for the different finishing methods showed that tensile strength was compatible for SLS and MGF technologies, with the highest value achieved for the power shot C method of SLS technology. The power shot C method had the lowest variability in the results, indicating the high repeatability and precision, while the power fuse S method showed the more significant variability, especially in the context of strain and elongation. The statistically significant differences in the mechanical parameters results between the machining methods indicate their influence on the properties of the prints, with the power fuse S providing the most uniform and reliable results. Components were selected for SLS and HP-MGF technologies to analyze PBF manufacturing process. The orthosis consists of the three components, and the upper and lower part, and the thumb grid. The orthosis model was saved in the STL file format and sent to the 3D printing machines. For SLS technology on the EOS machines, it is possible to produce 15 orthosis sets comprising 45 components. The entire production cycle is almost 35 hours. For HP MGF technology on the HP machine, 11 orthosis sets comprising 33 components can be produced. The entire production cycle takes almost 23 hours. A comparison of production capacity showed that HP system has a 30% higher weekly throughput than the EOS machine, while generating total production cost 33% lower. Production with the HP technology is more cost effective in the terms of the powder cost, and delivery time for finished orthosis make it more advantageous for medium volume production application. Although the EOS system enables more parts to be made in the one single, the HP remains the more efficient economic choice. Sorry. The weight of the plaster cast and 3D forearm orthosis were compared. The weight of the plaster is over 3 kilos versus 0.14 kilograms for the 3D printed orthosis. It means a 24-fold difference in the weight, considering by making an orthopedic supply using a 3D printing method, I get sufficient rigidity of the orthosis in stabilizing the forearm. Ladies and gentlemen, this is a high time to replace this 19th century invention of the plaster cast for the solution worthy in the 21st century. Thank you very much.
Thank you very much. Are there any questions to Andrzej about his cast? Because no one on the audience had any question, once again, thank you very much for your presentation. And our next speaker will be Jacek Łysawka. We'll stay in more biological topics. and he will tell about implementation of fluorescence lifetime imaging microscopy in the study of model cell membranes.
Thanks. Okay, thank you for your introduction, and hello everybody. As mentioned, I'm Jacek Łyskawa, and I'm here to talk to you about FLIM microscopy, fluorescence lifetime imaging microscopy, which is, I think, pretty cool idea. I use it to study model cell membranes, and I want to show you, well, how it can be used in research, not only for cell studies, but also in broader sense. Yeah, and let's go. So, where can we start? We can start at the beginning. I'll skip some old stuff, and we can focus on the 50s, where this idea was first introduced. But we had to wait another around 30 years for it to take off. We have some first results at the in the 1989. Well, they are impressive at the time, but for modern standards, I'd say they are, well, I think modern results speak for themselves. Okay. What exactly are we measuring? We are measuring fluorescence. So in simple terms, we can explain fluorescence as, let's say that a molecule is stealing the light. And after some time, it can give it back. So now the question arises, how could we measure the time it takes for this molecule to release this light? And what we can do is we can introduce some pulsed light that excites our molecule, and we can, using very precise detectors, we can measure the exact time it took to receive our photons. We repeat this process several times, and what we can see that each time the time needed to get this light is different. We plot it in a curve, in a histogram, and from this we can see that we needed that much time to get that many photons. Okay, let's take it a step further. What if we repeat the same process, but for each pixel in an image? That's where the FLIM idea comes into play. Okay. So how can we, what are we exactly doing? We need a microscope with a good electronics and a scanner. We need a sample to scan, and we need a pulsed laser. When we have all of that, we can get both intensity profile and decay matrix I showed you before. Now, to get the lifetime, we need to apply some algorithmic fitting, and for each pixel, we have a different lifetime. Quick note, we are measuring this thing, lifetime. What exactly is this? Why do we need it? Honestly, this lifetime is exactly connected to the energy levels of our system, and it's highly dependent on many environmental factors. So it's not like we only are measuring this lifetime, but we are indirectly measuring a whole lot of different factors. I will mention them later. So we get an image. So image is interesting because it shows us a spatial distribution of this lifetime, but that's not what we can get. We also can get the parameter histogram that shows quantitative information. Yeah, I know there is a letter mistake here. The quantitative information about how many of those lifetimes are in the picture. And let's consider that there are many components at play that are shining differently. Well, in that case, there is a cool way to present the data with a phasor plot, which shows both presents both new information about amplitude and phase, and is a nice visual representation about our data, for example, for clusters or for specific types of molecules. Okay, so I mentioned that we can have many compounds. Now, what if those compounds were interacting with each other? For example, one would act as acceptor, and one would act as a donor. So here there is this thing called Forster's resonance energy transfer, where only one molecule absorbs the light, transfers the energy, part of this energy, to another molecule. And what we can do is, using this FLIM microscopy, we can observe a drop in decay. Okay, now using this data, we can assess the efficiency of this energy transfer, and by knowing this efficiency, we can get the distance between those molecules. Okay, but now comes the problem, because as of now, I've shown you only those images, which are like frozen in time. But in reality, especially in biology, molecules are always moving. So what if I told you that using this FLIM, we can also measure how things are moving? That's exactly what we can do. But in this case, indirectly. This technique is called fluorescence correlation spectroscopy. And we are not exactly doing FLIM images, but because the FLIM is so advanced, we can, using the same things that we already have, we can measure this fluorescence correlation spectroscopy. We can use this FCS. So what we do is we excite some molecules in some area, and by measuring the changes in fluorescence, we can then get information how those molecules move. We get some nice curves, and we can get the information about diffusion. Okay, now moving on to model cell membrane studies. So when I talk about model cell membranes, or cell membranes as a whole, what I mean is that this part of the cell that is a division between the cell and the outer world. So it is made from many different molecules, such as many different lipids, some proteins, and many more, which are interacting with each other in many different ways. And as I've shown you before, lifetime is highly dependent on many factors, such as pH, viscosity, and using FLIM, we can detect those changes. So especially as of recently, like more than 10 years, there has been a lot of development in this field of study concerning cell membranes. And I believe that I have shown you now that FLIM technique is and will be very useful to apply in this field. Okay. To conclude, I'd like to show some advantages and disadvantages of this technique. So for the advantages, well, we get an image of fluorescence lifetime, which is of high resolution, not only a spatial one, but also on temporal one. Well, as well, it can easily be connected to other methods, such as FCS or FRET, and doesn't really depend on intensity of fluorescence. Yeah, and as you probably know, it's not widely used yet, mainly because of its price, but also the data it collects is pretty large, because we get an image with intensity and all of those curves. So we cannot really go to the lab and do like 1,000 pictures a day. It's not really that possible, I'd say, for now. Yeah, and to get those lifetimes, we need those algorithms that can be dependent on many factors, such as how many compounds there are, and so on, so on. And the results can vary if we are not careful. Okay. Thank you very much for listening. And if you have any questions, please feel free to ask.
So, if I may, I have one. Thank you for a very interesting presentation. So I wonder, when you're taking this, your measurements, are you doing it for a given set wavelength, or like just measuring the whole intensity, whole intensity of light?
Okay, thank you for your question. So to go back, for example, to the start, we excite our molecules in a range they can be excited at based on absorption spectra. And so what we get is, I didn't have to go that far. What we get is a lot of different light, but we can, we are not really measuring types of fluorescence.
Okay, so for example, if you have different bands in your spectra, can you separate them and take the times of these specific bands, or you just have one time for all of the spectra?
Yes, we can. We can, for example, using this technology, we can separate the light that we are receiving into, let's say, one wavelength and another one, or maybe not only two. Maybe there are 10 or 15 different wavelengths that we are receiving, and modern solutions allow such measurements. Thank you.
Maybe I will ask you something, because some of the disadvantages that you told were that the technique is pretty expensive. I suppose that it's because not only because it's uncommon, but also because just the measuring setup is complicated. Can you tell us something more about how this experiment is performed? Like what you need to measure, because it's a very interesting technique that, as you said, would be probably in future used more often, not only for the biological stuff, but something more about it.
Of course. So I will move back here. And this setup has a lot of like a wiggle room, I would say, for depending how much detail we want to, how much information we want to achieve. For example, one thing is that, well, we need a laser, but there are many types of laser, and if we want to get a very precise, nice shaped laser, pulsed laser with short impulses, then it's probably going to be expensive. That's one way to look at it. We need to introduce it to the system, and then it's a pretty simple and yet not so simple way to precisely scan this area pixel by pixel to collect this data for every pixel and cut the wavelength of the laser beam we apply, and to collect only fluorescence. Does that answer your question? Thank you as well.
Okay. I would like to invite our next speaker, which is Piotr Kałuziak. And
Hello everyone. My name is Piotr Kałuziak. I'm from Poznań University of Technology, and today I will tell you about study of fabrication of indium antimonide thin films on gallium arsenide substrate in potential application for Internet of Things. So in the next 10 minutes, I will take you for a trip through my studies, and starting from Internet of Things. IoT, it's a great idea, can connect physical objects, can connect anybody with any device, with any service at any network, anytime and anywhere. For example, you have security camera on your apartment and you get notification that detect motion on sound, and you can check that, send you a screenshot that your cat is playing around your inside your flat. Internet of Things consists of 4 major areas, and today I will focus about sensors. Sensors gather data, produce data, process data through some connections networks. And speaking about sensors, I'm focusing on using indium antimonide thin films in modern hybrid circuits. I want to use them to fabricate magnetoresistive sensor, and also in advance I want to check if it meets assumptions of physical unclonable functions. So to achieve this, I set myself 3 goals: to design a hybrid planar structures. Next, developed a process for structuring indium antimonide thin films, and to perform electrical characterization of fabricated structures. These studies take place with cooperation with Division of Surface Physics and Nanotechnology, and also with Wielkopolska Centrum of Advanced Technologies. As my material, I choose continuous layer of indium antimonide on gallium arsenide substrate. Indium antimonide is a semiconductor and has a narrowest energy band gap within the all semiconductors at level 0.18 electron volt, and also high electron mobility, 77,000 square centimeter per volt second. I divide methodology to 3 steps. First step, it's for generate continuous layer. Second, to from this continuous layer achieve segments which will be our active channels, and at the end, in third step, I short circuit these segments to create sensor, strip magnetic sensor, exactly. To generate continuous layer, I can use method as like molecular beam epitaxy. This is great method. We can achieve high quality thin films using this method, but this method is very expensive, demanding, time consuming. And also I mentioned that I want to check assumptions of physical unclonable functions. So I don't need perfect thin films. I need some faults inside my structure, inside my thin film. I need some defects. So that's why I choose a flash evaporation method. This method is less demanding, less time consuming. Here I need a vacuum at level only 10 to power minus 5 millibar. Of course, obtained thin films are not as good as obtained by MBE method, but they are this method is reasonable choice for laboratory application. So a few words about this method. In this method, I deliver grains of indium antimonide and antimonide through shoot mechanism into tungsten strip. When grains heated tungsten strip, they flash evaporate. Then vapor of indium and antimonide reach the heated substrate and start to generate a continuous layer. Next two steps, I was inspired by approach for graphene structuring active channels, and in my approach, I covered indium antimonide layer by photoresist, then using maskless optical lithography, I remove this photoresist from a very specific area which I choose, and then I protect indium antimonide layer in places when I want to remind this after buff acetone. So using acetone, I remove indium antimonide and remain only in places when I want to get active channels. After that, using one more time optical lithography and also DC magnetron sputtering, I deposited metallic electrodes using for short circuits these active channels. Here are some results. On the left, we can see a sample coated by photoresistive substance. In the middle, we can see sample after bath in acid, and on the right, after lift off process. Also, I perform some images using EDS, SEM, and IFM. EDS brings me information about proper removing indium antimonide from substrate, and we can see that we create interface between layer and substrate. Also, we can see that on SEM images and focusing on layer and substrate, and also we can see fault between layer and substrate, which bring us information about size of this layer, about this thickness. And also using AFM, we can also check that topology is homogeneity here. When I check my active channels, then I had to design some projects to deposit electrodes here. And first and major projects is on the left, where we can see strip magnetosensor with extra electrodes used for electrical measurements. On the right, in the middle, we can see advanced project which helped me to measure influence of electric contacts in this structure. And on the right is final design of matrix with 36 segments of indium antimonide, which will be used for studies about physical unclonable functions in this material. As results, we can see that strip magnetosensor responds in magnetic field, which brings information that this device can be used as a magnetic field sensor. But what is more, I checked influence of modifying this layer of material. And as you can see, when we change surface, when we change size of a layer, only to moment when we don't have to use electric metallic electrodes, parameters remain as nearly same. After using electrical metallic electrodes, parameters change, which bring us to some conclusions. So indium antimonide on gallium arsenide material can be fabricated and modified for sensitive magnetic field sensor. And it's crucial to examine the effect of metallic electrodes here. Also, this strip magnetosensor can be adapted into the grid matrix format, and this adaptation can be potentially used for Internet of Things due to PUF properties of the material. And at the end, I want to present you a group of people involved in these studies. And this is the end. Thank you for attention and feel free to ask questions. Yes. Not yet, because now for this at this level we just checking material properties. We not yet built a sensor. Mhm. Next step is to more advanced measurement about influence of this electric of these metallic electrodes to check influence on whole structure. So after that, I can measure properties of only indium antimonide, including influence of these metallic electrodes. And at the final step, I want to measure this matrix of 36 indium antimonide segments. Thank you.
Thank you very much. Our next speaker is Edyta Chłopocka, and she will talk to us about the film of perovskite oxides.
Thank you. Thank you. Good afternoon. My name is Edyta Chłopocka, and today I am doctoral student from Poznań University of Technology. And today I would like to talk about the influence of the spin coating deposition parameters on the properties of thin films of perovskite oxide lanthanum ferrite. So first, about motivation. Why I am interested in these materials? Well, there isn't a day where we aren't hearing about the energy crisis or the climate change. So of course, people are more and more interested in alternative energy sources. Unfortunately, silicon solar cells, which are commonly used, are reaching their full capacity, their full efficiency, because of the theoretical efficiency is about 30%. It was calculated by Shockley and Kaiser. It is called Shockley-Kaiser limit. So researchers are looking for different devices for different materials. And here comes the perovskites, which have potential to exceed this 30% limit. As far as I am aware, they reached recently like 26%, so they are getting really close. When we talk about perovskites, about these high efficiency perovskites, we are talking about ABX3 compounds, where in the place A side, they usually use an organic part, and in the B side, lead. So this creates its own set of problems, because the organic part obviously lowers the heat resilience of these devices, and lead is also dangerous. If any leakage were to happen in the environment, it's difficult to recycle. So in last 4 or 5 years, new kind, not maybe new, but another type of perovskites were taken into interest by researchers, and these are perovskite oxides. They can take on various roles in generating clean energy. They have been so far commonly utilized as powders and solid oxide fuel cells, and these same oxides powders have been used in as porous photoanodes in disynthesized cells, and also people started making calculations, numerical calculations to include perovskite oxides as a whole transport layer or an active layer in solar cells. What I'm doing is I am synthesizing and depositing lanthanum ferrite using wet chemistry, so Sogel process. And I am producing powders, but I also get in the middle of this process and deposit aged sol onto a rotating substrate to create thin layers of material using spin coating technique. This method is quite cheap. It doesn't require expensive equipment, so it can be quite primitive, but because there's lots of variables in play, it is very important to very focus and look into each variable that we can influence. For example, we can change the precursor. Here I used nitrates and acetonates of lanthanum and ferrite to create these layers. What we can also change is the time of aging of this precursor, also the amount of material we are depositing, the speed of the rotation, and obviously when we are coating, we can coat it numerous times and then calcinate it, anneal it to ensure that it is a crystalline layer. So we can do the deposition, and sometimes we can see just looking at it under the microscope or just looking with our eyes that they do not look pretty. They are not the best quality. If the concentration is not right, we can end up with these comet streaks, which are which can be several hundreds of micrometers in diameter. If the concentration is too big, on the other hand, we can end up with deposited material in the with big chunks of deposited material. So when we find the exact spot, the exact solution, then we can end up with very uniform, pretty thin, here we have 25 nanometers, thin layer of material. I've performed X-ray diffraction on the powders prepared with the solution that I deposited to see that we've obtained the right structure, which is orthorhombic structure typical for these materials. And also we can perform this powder synthesis many times, differentiating, for example, here the stabilizer content to ensure that we use the right amount, because if we do not use the stabilizer, it can be really hard to get a crystalline layer. If we use it too much, then we again will destroy the crystallinity. When we perform the diffraction measurement on the layers, we do not get a very strong signal because these layers are polycrystalline. They are deposited on quartz glass. But when we compare it with the previous one, we can see the same 200 peak and also several weak reflections. So we did get the right crystallinity. And even though we cannot see these layers with our eyes, we can look under the atomic microscope, atomic force microscope. And here we can see that depending on which precursor we choose, we can get very low roughness, below 1 nanometer. Now we can also utilize absorption. And in using this method, I found the right aging time. As we can see, between 24 hours and 48 hours, it takes very long to ensure that the oxygen bridges are built up and we get the right optical behavior, which is this double absorption edge typical for perovskites. Using the absorption measurements, we can obviously do the dot plots and find the transition energies, which are in correspondence with the theoretical values found in literature. What I didn't include is that if we do the same measurement for the acetylacetonates, it turns out that the aging time is significantly shorter. So, and now for the structure, this is how a perovskite structure looks like. This is the perfect perovskite structure. So we have lanthanum in the middle. It is surrounded in a cube by ferrites, and each ferrite is surrounded by a oxygen octahedra. But when we look at the calculated ABC lattice constant, we can see that the C is elongated. It happens when this atom and this atom, so A and B side atom, are their ionic radii are not matched, and this causes the elongation. And these octahedra are very important for us when we are looking at the Raman spectra, because they are we can see them very well there. So we can see their bending, their stretching, their rotating, and this can inform us about the structure even further. When we look at the powders, we see several modes. But unfortunately, when we look at the layers, once again, because they are very thin and they are polycrystalline, we can see only the 650 peak and the 1300. But when we do the analysis, we can see if the deposition was successful. We can do Raman maps, and also we can cross-reference them with, for example, photoluminescence to analyze the defects in the structure. To conclude, perovskite oxides are not new, but still very exciting materials, which can find new applications in clean energy harvesting. Utilizing sol gel and spin coating allows to create thin, uniform layers if we find the right properties. And the lanthanum ferrite layers deposited in this study have been obtained using two different precursors, which resulted in different topography, but similar optical response. Thank you for your attention. Yes. Mm-hmm. Yeah, so basically, when I was doing the initial research, I was very drawn by these publications that I thought about at the beginning. And so basically, I was looking at them, I was looking which materials are finding like experimental interest by people. And also, I've read that lanthanum, among other rare earth materials, can be very beneficial for the electrical properties. So it can be very beneficial if not as an active layer, then at least as a whole transport layer in this. Yeah, initially I was thinking about lanthanum based using ferrite, using manganium, and so on and so on. but it turns out that, like I said, these layers are polycrystalline. They are hard to detect using Raman, and I found that lanthanum ferrite has many modes, so that allows us to really analyze what is going on with manganium, for example. The modes are very weak and they are very broad, so they could not be detected due to the background from the substrate. And that would be just, we would have to look for other techniques of detection, basically. Thank you.
Thank you very much. And our next speaker is Ivan Davinenko.
Thank you. Okay. So apparently these cats have something in common with today's topic, and as you can see, their tails are entangled. So my name is Ivan Davidenko, and today I'm going to talk about entangled state generation in the vicinity of exceptional points, and also I would like to address the question whether it could revolutionize the quantum computer. So I would like to start with explaining what is quantum entanglement. So imagine yourself some very modern quantum bakery that produces quantum cakes. So if this orders gets an order for 2 cakes, it could realize it in 4 different ways. So if the probability of getting round or square cake is the same, we could get one of these 4 probability with chance 1/4 each. So we could write such state of this system of this order as just product of 2 states of each cookie. But if we have maximal entangled state, we can't write we can't write the state of the whole system as the product of state of different subsystems like first and the second cookie. And the next thing I would like to explain is petysymmetric systems and exceptional points. So imagine yourself 2 systems. For example, this could be atoms, and these atoms are connected with a tube, and energy from one atom, for example, atom B, could go to atom A, and one of the atom has gain of energy from the environment, and the second atom loses its energy. So what would happen if we were to reflect this system in space using, for example, mirror, and also change the direction of time? As you can see, we will get the exact same system as A and B are indistinguishable. So mathematically, you can see that if we apply operators of spatial and time reversal, we would get the same Hamiltonian of the system. And the exceptional point of such PT-symmetric system is the point is the parameters for which eigenvalues of the system are the same, and also eigenvectors are the same and parallel. And we started our work by finding article in Physical Review Letters that told us that we could actually speed up generation of entangled state in qubits in the vicinity of so-called exceptional point. So authors suggested that by slightly shifting of this exceptional point, we could get much faster generation. So in their case, they could get this generation in only 5 microseconds, whereas in Hermitian case, when we don't have this damping gamma, it would take this time would be proportional to 1 over iot, where iot is coupling force. So for our system, it would be around 1 millisecond. So it's 1,000 times faster. So you could imagine if we were able to to make this operation of quantum entanglement 1,000 times faster, it would really enhance quantum computing and quantum computing. So, and actually, we were able to recreate these results. And as you can see, we've got the same graph with entanglement generation in time, and we were able to obtain the same maximum for some given parameters of the system. And we could think that actually this works, and maybe we could use it in real quantum computers on real qubits, but until we use another method of solving this system. So as you can see, we've got this beautiful plot where concurrence or entanglement is continuously zero, which means that quantum jumps that were taken into consideration by using so-called master equation kill the entanglement. But why? So let's apply annihilation operator of one of the atoms on the system state in the arbitrary moment of time. As you can see, after application of this reduction, we can get state of the system as just the product of states of two subsystems, first and second atom. So the state is basically separable and it can be entangled state. So as we can see, quantum jump just destroys our attempt to create entanglement in such system. Why is this model that was described by these authors doesn't reflect the reality? So to address this, I propose to return to transmon model that actually qubit model is based on. So transmon is artificial atom that has 3 energetic levels, F, E, and G. If we use so-called post-selection and discard all instances when there is quantum jump from level E to level G occurring, we could describe this system with using non-Hermitian Hamiltonian with only 2 levels, F and E. And level G acts as a continuum. But let's actually use this original model in our master equation and try to see what would be probability of no emission. It means that there would be no quantum jumps. As you can see, for the time of maximal entanglement generation that was given in this article, this probability would be the order of 10 to the power of 10 to the minus 15. It means that we would get one successful generation attempt in 100 trillion failures. So it would take us around 30 years to actually succeed in doing this. And as you can see on this graph, it's evolution of energy level occupation in time. The occupation of level G actually abruptly rises over time. But actually we could try to do this by using post-selection and discarding all attempts when we have quantum jump, and we could see whether even this simple model could work in some special cases. So as you can see, when we discard all quantum jumps from level E to level G, we have this probability, this occupation of level G equal to 0. And as you can see, by comparing our result for post-selection to our previous result for solving Schrodinger's equation for non-Hermitian Hamiltonian, it's actually the same. But as you can see, we were able to achieve only 2 microseconds because after this probability drops significantly. And also, authors of original article didn't use other parameter called gamma f, which describes dumping of energy from level F to level E. And actually, you can see that even using very small gamma f, which is 3/100 hertz, 1/microsecond, it significantly spoils generation of entanglement, since we can't get the maximal value for the given time. And to summarize my talk, I would like to say that actually we were able to achieve the same result as the original authors, but also we have found that by using more complex model, by using so-called master equation, we were able to show that quantum jumps killed the attempt of generation of entangled state, and actually they a bit lied in their article by saying that it could be used in real quantum computers, since it has no use in the current state. But if we actually use post-selection, yeah, we could achieve the same result, but we would need to repeat and repeat this process, which would take much more time than like the classical way of generating entanglement. And I would like to give special credits to our research group, which are our chief professor Adam Miranovic and my scientific supervisor Dr. Grzegorz Himczak. And thank you for attention. Stay entangled.
Thank you very much for your speech. Are there any questions? I think only one such a theoretical speech today. Okay, if no one has any question, I would like to ask you one thing, because as you probably saw, most of us here are experimenters, so we are so used to experiments that this kind of physics is far away from our look. So what are the ways of, because there's like basically theoretical work, yes? I see that you told that the paper that you were evaluating wasn't right, so it doesn't work, but so even in the experiment it wouldn't work. But how do you perform such an experiment? Is it possible to experimentally evaluate such a thing?
You know, this in original article, they proposed it as the solution for probable use in like real quantum computers, and probably they tried to use the same characteristics, and I think that it could be this experiment could be conducted on quantum computer of, I don't know, IBM, for example. But actually, as I said, it would give no result, since you would need like 100 trillion attempts to do it. If you calculate, it would take roughly 30 years to just achieve this one successful attempt. So unfortunately, we needed to show this. And
to them.
We're trying to now. We conduct another research. We're trying to find some use of this. Maybe we could change something, etc. So.
Thank you. So we have our fingers crossed that they will read your work and not sit in the lab waiting for the entanglement to occur, because it will not. Okay. Thank you very much. Ivan was our last speaker for this panel. So I would like to thank every speaker of this panel and invite you to the poster session. Thank you very much.